We're good. Okay, cool. Thank you so much for coming here. I think this is a very busy time. We're all exhausted. Exams have been tough. But we're all here preparing for our D84 final. And this reminds me very much of the tutorial. So we're going to start in the same way as the tutorial. It's me asking questions and you giving me answers. But this time, thanks to AMACSS, we have some chocolate that you can win if you give the right answers. Sure. Okay. So today, not sure where these lights are. Okay. So today we have two things to cover. One, we're going to do a little bit of review. Review meaning we're not going to teach you the concepts. I'm assuming you all know the concepts. But this is just a recap kind of to see where we are at, see if there's any gaps in our understanding. And then we'll do the sample final, which the professor posted. Let me tell you beforehand, the sample final is kind of a little bit easy. It is very similar to the tutorial questions. Some of the questions are repeated, so you might already have the solutions. But if you stay till the end, we have something to give you back as a token of appreciation. So stay tuned. Cool. So for the first part, I'm going to be doing the pre-midterm stuff as we did in the tutorials. And Malhar here is going to be doing the post-midterm stuff as we did in the tutorials. And we'll be starting with search. Okay, the way we're going to do this is we're going to talk. We're going to have conversations about why, what happens. And then this slide is everything that's on the slides is basically a practice question in that whatever field that is. You can either do this, you can make me do this, I'm here to do it. But please know that you have 3 hours of time and you want to spend it very, very sparingly, because you want to spend time on the later part, which I'm assuming a lot of people have questions about. So if you feel you're kind of confident about search, we will not spend time solving this problem. But if you want to revise UCS or A star, I can do that. But let's, before that, start with our definitions. Can someone tell me what is an intelligent agent? I feel like I'm repeating this from week 1. An intelligent agent. Okay, so in tutorial, I gave infinite time because we had that. Right now, we don't. So every time you don't answer a question, a chocolate comes to me. Okay, cool. So an intelligent agent is an agent which can sense the environment and based on the state of the environment, take an action to achieve a goal, a predefined goal. Perfect. A state. What's a state? Yeah?
It is a position but is possibly obtained.
Okay, perfect. We had a little bit more broader definition for this. It was a particular set of, go ahead.
I was going to say a possible configuration of the environment.
Exactly. So it was a particular assignment or configuration of the state variables. What is a world space? A world space. Okay, the set of variables that basically encompass the world, anything and everything. So rain in New York, a stupid storm when I was out cycling for 2 minutes here, whatever. So state space is the set of states that include every possible system configuration. What is a state space then? We define a world space. What is a state space? Anyone? Okay, a state space is basically a subset of the world space, which is the set of assignments or configurations of the variables which are under consideration. So those variables will have a direct effect on us achieving our goal. So that's what we need to consider. Perfect. What is a search problem then? What are we trying to do? Go ahead.
Typically, given a start and a goal, it attempts to find the shortest path between the start to the goal.
Sure. That's one formulation of it. Essentially, so a little bit motivation behind this. Basically, AI researchers whenever in the 50s, 60s, were thinking of, hey, just like a theory of everything, can we have a way or an algorithm to formulate every problem that exists in the universe? But even though that was a research question, they came at something called a search problem. A search problem is, in this case, a deterministic single agent problem where you have a finite space, and in that finite space, you have a finite solution. Perfect. Cool. So a search problem, again, consists of states, actions for an agent, and the success. So all the actions might not be, so the set of actions could be large. Even the set of states could be large. So sometimes what happens is, instead of representing the entire graph, what we do is we represent a subset of the graph, but we show a function, we create a function which gives, given one state, the next successor state we can get. So instead of storing all the neighbors in our computer, we can just store the function itself, and whatever input state we get from the user, which the user should give us, we give the next successor state we can reach. Perfect. What is the solution to a search problem then? So as he said, it was the path. We want to reach a goal from the start node. So it is the path that we take from the start node till the goal node. That's our solution. OK. So that's basically definitions. Go ahead.
For the previous question, could you also formulate as the set of actions taken to get the goal?
Yeah, set of actions too. Exactly. Oh, that's the definition I did in tutorial. So yeah, that makes sense. Cool. Honestly, yeah. Sorry about this. I've been missing out. Oh, my bad. And one more. OK, cool. Now, we're going to revise all the algorithms. So the professor posted some things you should know for the final. In a way, those things are at least what you should know for the final. So whatever I'm going to give you now is basically those things, plus a little bit more. OK? So for any general search, what we're trying to do is a tree. We're trying to create a tree so that we can abstract it and then use the algorithms that we know to find a solution to our search problem. So in this case, if we are using a tree, we start with the initial state as our root. Okay? And from that initial state, we keep searching in a way which our strategy tells us. A strategy is basically an algorithm. It could be DFS, BFS, UCS, whatever. So based on that strategy, we start expanding the node. Once you expand the root node, you get the successor nodes. Then you start expanding successor nodes or whatnot based on the strategy. If at some point you reach a node where you perform the goal test, okay? Sometimes, instead of giving you the goal state directly, the problem will give you a goal test so that you perform that goal test on a certain node and determine whether that node is a goal or not. Okay? So while we are finding and expanding, using our expansion function, we do the goal test. If the node is a goal, we stop and return that path, or we keep searching continuously. Cool. So that is a general tree search algorithm paradigm. Now, based on that, we will be doing two kinds of search. One is uninformed search, and second is informed search. Uninformed search refers to search which is done blindly. Algorithms that we learned in, I think, B63 were basically uninformed search algorithms. DFS, BFS, anywhere where you do not consider the cost is uninformed search. Even UCS, though. UCS, anywhere where you don't consider the cost from the current node to the future. So anything about the future you don't consider, that is uninformed. Where you consider whatever information is available to you, that is informed. And this is uninformed. OK. So BFS, DFS, UCS, these are uninformed search algorithms. So for DFS, our strategy is essentially keep expanding along one particular node. But the strategy is to expand the deepest node first. Okay? We are trying to find the node at the maximum depth, and then come back till the time we find it. So if we were looking at this graph, what DFS would do is, let's say we are at the start, then we start with B. Or let's actually start with A because we'll have alphabetical order as our tiebreaker. So start A, then we expand neighbors of A, C, expand neighbors of C, and then reach the goal node. If we were doing DFS then, is it complete? Do you remember what the definition of complete is? Yeah, go ahead.
It is not complete because there might be like infinite depth.
Yeah, there might be infinite depth, there might be cycles. There was one thing as well. So a completeness, though, is the ability for the algorithm to return a solution if there exists one. Okay? If your DFS gets stuck in a cycle, or it goes till infinite depth, which possibly might occur, you would not get a solution. So in those cases, it is incomplete. But if there are no cycles, if the depth is finite, then this is a complete algorithm. Perfect. Is it optimal? We saw from the start node, we reached the goal node. We didn't even explore the other paths. So is this optimal? Yeah? No? It's not optimal. Perfect. Sorry. Oh, good one. OK. What is the space complexity of this DFS? Go ahead.
B times M.
What is B and what is M?
B is the branching factor, M is the depth.
Perfect. So branching factor is basically from one node, how many successor nodes you have. And M is the maximum depth that you can get. So if, again, the depth is infinite, our complexity is infinite. But if the depth is finite, we have O of Bm. Space complexity. What about time complexity? Anyone? OK, the time complexity is order of b to the power m. Can someone tell me why? Go ahead.
Because in the worst case, you have to search every other node until you find it.
Exactly. That's what DFS entails. So we're counting the number of nodes, and we have branching factor raised to the power m nodes. OK, so that's DFS. One more for you, and one for you. BFS. Perfect. In the BFS algorithm, what is our strategy? If it was deepest in the depth first search, what is breadth first? Go ahead.
Explore all the closest nodes.
Yeah, closest nodes or shallowest nodes. Basically, you're exploring the breadth first. Essentially, that is the strategy. Any idea what data structure you would use for this?
Q.
OK. Why a queue?
Because we first like enqueue the neighbors first,
Mm-hmm.
and then like dequeue them. Basically, first in, first out.
Exactly. We need the first neighbors to go in and then come out before we go to other neighbors. So that's why we use a queue. It is complete, as we know, because it will search for every node if there's finite depth. And if a solution exists. If there's no solution, of course, this algorithm might just search and find, like, hey, no solution. Optimality. Will this algorithm be optimal? Yeah?
Optimal only if the all the edges that have a weight of 1.
All the edges have the weight of 1, exactly, because it will find the shortest path, but essentially what you need to do is consider the cost when you're doing such algorithms for graphs like these. So, OK, that is cool. Optimality is done. Space complexity. Here, we're storing all the nodes till the time we find the first solution. So the space complexity for this is order of b to the power s. So we're counting the number of nodes till the shallowest solution. S is the depth of the shallowest solution. So space complexity, order of b to the power s, and time complexity is the same. Once you find the shallow solution, you're done. So that's breadth first search. Another one we covered in tutorial was iterative deepening search. This was a combination of breadth first and depth first search. In iterative deepening search, you have a particular k. This k is the level that you will explore till, and then you return. So you do depth first search till the level k, and then come back. So if k is 0, you explore the root. If k is 1, you go to the left part of 1, then go to the next one, and come back. Sorry, you don't go back. This is not back. So you just go to the next one. If the depth is 2, you go to the second one first, then the neighbor, then go up, then the left, and then the right. So essentially, it's a mixture of DFS and BFS. The implementation is a stack for this. Completeness, again, if a solution exists. Optimality, if the cost of all actions is 1. So essentially, we're finding the shortest path again. So the cost, if the cost is higher, then we might not find the shortest path. Space complexity, here we're expanding, again, just as BFS does. So, sorry, BFS does. The order of B times M, where B is the branching factor, and M is the maximum depth of the search tree. And the time complexity was O to the power, order of B to the power M. It's the same thing. All of these things are basically in your slides, so I'm not writing them down or showing them where you can take a picture or whatnot. Also, yeah, you will know later why I'm not doing that. Uniform cost search. Now that is the algorithm we learned for the first time in this course. Can someone tell me what algorithm is uniform cost search like? It was derived from something. Yes?
So what you do is you basically use a priority queue based on the weights of the edges. So
Exactly.
explore the least weight edges first.
Yeah, we explored the least weighted edges first. If you took B63, C783, you came across something called Dijkstra's shortest path algorithm. Very, very similar to this. Essentially, this is what we do in that. The only difference is here we are trying to find a goal. There we're trying to find the shortest path to something from a single source. So for uniform cost search, the strategy is we expand the cheapest node first. So for breadth first search, it was shallowest node first. Depth first search, it was deepest node first. For iterative deepening search, it was the deepest node till a bound k. And then for uniform cost search, it is the node which is cheapest first. So completeness, if a solution exists and the minimum edge cost is positive, then this will find a optimal solution. It will find a solution. In optimality terms, it will always find an optimal solution if there exists one. Space complexity-wise, we are doing order of B to the power C star by epsilon space. Can someone tell me why? This was taught in lecture. I don't know if you guys attended or know what was happening there. Where C star is the solution, optimal solution called C star, and epsilon is the least edge cost. So again, I will repeat, the uniform cost search, where we find the cheapest node first, has a space complexity of order of B to the power C star by epsilon. Okay? The C star is the depth of the solution, the optimal solution, and epsilon is the minimum cost of an edge. Any idea? Very intuitive. Go ahead.
No.
Oh, you have no idea? Okay. Go ahead.
If C star over epsilon will give you like the maximum number of steps to the least cost node?
Exactly. So essentially, if you remember lecture or if you see the slides, there's a beautiful diagram in there which shows that you explore all the nodes till a particular cost is reached. So it's like contours of solutions. So that's why C star by epsilon nodes will be expanded in the worst case. C star is the optimal solution depth, and cost, not depth, cost. And epsilon is the again least cost edge. So if there's C star cost that you have to cover, and you have each edge costing epsilon at the least, then C star by epsilon is the maximum number you can get of the nodes that will be expanded before that. Time complexity, hence, is the same thing, order of B to the power C star by epsilon. Perfect. Do you want me to run UCS on this? How many people? Just raise your hand. OK, thank you so much. A star search. Now the strategy here is to make our UCS a little bit more optimal. For this, we are using a little bit of information regarding how much distance or how much cost will I have to incur to reach the goal from my current node. Another version that was kind of similar to this, but was not very effective, was greedy search. In greedy search, we just considered that. In A* search, we consider the distance from the start node to my current node and from my current node to the goal node. The current node to the goal node is a heuristic. It needs to be admissible. Can someone tell me the definition for admissibility of a heuristic? Go ahead.
Heuristic is admissible as long as its estimation of the cost from that node to the end is lesser than the actual total cost.
Okay. That cost to the end. I think to the goal?
Close to goal.
To a goal that is closest, okay? I feel like a bunch of people messed this understanding up at the start and made mistakes regarding your first problem set submission. But essentially what happens is you could have multiple goals. What your heuristic should have as in terms of admissibility is that it should be, first of all, greater than 0. It cannot be less than 0 because you're incurring a cost. And it should be less than the distance or the cost to the closest goal, not any goal. Or also it's not the closest goal, it's a closest goal. Multiple goals can have the same closest distance, all right? So keep that in mind when you do A* search. That's admissibility. And also, basically, an admissible heuristic never overestimates the cost of reaching a goal. That's what admissibility means. A heuristic is consistent. Now, this is a definition which was kind of explored in lecture, but it was a little bit technical. There was something about an arc. If you remember the diagram, it showed A, B, and C. There was a triangle inequality shown. But what it was trying to say is a heuristic is consistent if from neighboring nodes A to B, let's say A and B are two neighboring nodes, the heuristic difference or the step cost never overestimates the actual step cost. So the heuristic from A till the goal does not overestimate the heuristic from B till the goal. So the difference should be, the first should be less than the second. If you have questions about these, I would recommend you to look over the slides. There's a beautiful diagram that just gives you the intuition. But I think it is also important for you to know this for the exam. Just saying. Cool, completeness. If a finite solution exists, A* will find it. Optimality, if the heuristic is admissible, A* is optimal. Space complexity, same as UCS. Time complexity, same as UCS. We're talking about the worst case, so heuristics don't change the space complexity. Okay, that is also a thing you should keep in mind. A heuristic will not change the worst case complexity of any algorithm. A heuristic is just for improvement in performance in practice. It might change the average time complexity for an algorithm, but that's not what we're talking about. This is also true for, I think, constraint satisfaction problems where you have heuristics that we will cover when we get to it. Okay, so that was A* search. Last algorithm that we kind of explored in tutorial, local search. Local search, dumb search, whatever you want to call it. We explored something called hill climbing. Remember that diagram that I showed you? Essentially, what we are talking about here is where you start with any node, then you explore the successors. If the successor is better than the current node, great, go to the successor. If it is not better than the current node, hey, current is the best I can do. That's what the search does. You keep doing this multiple times, and maybe you'll find a solution. So if I'm saying maybe you'll find a solution, can someone tell me what would be the time complexity in this? Okay, first of all, is it complete?
Well, depends on the heuristic.
There is no heuristic. It's just the hill climbing, vanilla hill climbing. Is it complete? Is it guaranteed to give me a solution? Go ahead. No, exactly. It won't give me a solution always. Is it optimal? If it finds a solution, is that the optimal solution always? No. So it's not optimal, it's not complete. Then the time complexity ideally is O of infinity, because maybe you'll keep searching forever and you'll get stuck in the same local optima forever. Who knows? That's why you're not guaranteed a solution in a finite amount of time. Space complexity, here we only keep the current node and the successors of a node. So either you can you can choose to store the successors. In the algorithm that the prof showed, we just compared the successor and stored the best one. So if we're storing only one, let's say, node, then basically our space complexity is 1. That's all about hill climbing and local search. Any questions about search? That is it. Also, I had some stuff for A star, weighted A star, greedy search. Anyone wants me to run this algorithm? OK, cool. No questions about search? I am moving on. 3, 2, 1. Perfect. Oh, anyone who didn't get chocolates? I kind of lost track. Anyone else? Did you answer? And I'm sorry, guys, I forgot. Just whatever. Answer more questions. OK. Next topic. OK. Also, this some people asked me after the tutorial to get a picture for. This is basically comparison of all of them in one, if you want to memorize stuff. This also doesn't have the C star by E kind of optimization, but yeah, go ahead.
I forgot. Does A star need to be consistent to be optimal, or just invisible?
Consistency. OK, that's a actual question in the slide. Does consistency imply admissibility?
I think so, yeah. But I don't know if it's needed.
It's not needed. If one is a smaller condition for the bigger, consistency implies optimality. Consistency implies optimality, yes. So if something is consistent, it will be optimal. Admissibility, I'm so sorry, I'm just using words. Consistency implies admissibility. So admissibility is a stronger condition. As long as it is admissible, thing is basically optimal. A star search is going to give you an optimal result. So if it is consistent, it will essentially give you an optimal result.
Is it possible for it to be admissible, not consistent, and inoptimal?
Admissible. If it's admissible, it's optimal. If it's admissible, it might be the case that it's not consistent. Yes. Go ahead.
I think you need consistency to be optimal in graph search, and then admissibility is okay enough for tree search.
Admissibility is okay for tree search, and you need consistency in graph search. Yes, 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 yes. That's correct.
Consistency, I think, is a
Stronger one. Yeah. Consistency implies admissibility. Yeah. That's what I meant. Consistency implies I will just draw it. It's easier. So if consistency implies admissibility, there are a set of heuristics that are basically admissible, and within that, some that are consistent. OK? Does that clarify? OK. Sorry, guys. If I misspeak at some point, just ask me questions, OK? Go ahead. I will post the slides on mostly Piazza. OK. Perfect. Constraint satisfaction problems. Now, constraint satisfaction problems came to be as an extension of search problems in a way. Here also, we use a tree search paradigm. However, what we're trying to find is if there exists a feasible assignment to a certain set of variables. Cool. Anyone want to define a constraint satisfaction problem for me? Or it's fine. I'll have the chocolate. A problem where every state is defined by variables xi with values from domain di, and the goal test is a set of constraints specifying valid combinations of values for subsets of the variables. Okay. Basically, what you want to focus on is we are trying to find assignment of values from domains di's to variables xi's such that a set of constraints, that is the goal test, is satisfied. Cool? Very simple logic. The algorithm that we try to use for this, or we introduced in this class, is backtracking search. I think all you need to do is understand the algorithm. I wouldn't say you want to memorize all of the algorithm. It's kind of, you can come up with a pseudocode on your own. But what you need to understand is why the improvements on that algorithm work. OK, whenever you see a CSP, I want you to follow this template. OK, for the problem set, a bunch of people kind of lost marks because they missed some parts of this template. So you start always with the variables. Then you come up with the domains for those variables. Each variable will have its own domain. If you feel like all of them have the same domain, you should write proper logical statements saying that. OK, constraints should be, in this case, it is just whatever. Constraints are constraints. Some constraints might be implicit. Some constraints might be explicit. I will kind of highlight this again when we come to the paper solving part, because that question has those. But it would be great if you could write them separately so that we know you have interpreted the question in the right way. It is also easier for us to grade. Lastly, we want to find the solutions. Solutions are assignments of problems such that the constraints are satisfied. Enhancements we see for backtracking, again, forward-checking constraint propagation. I will come to those. Can someone give me a basic idea of what backtracking search does? Or should I explain it? Go ahead.
So we just keep searching, and then when it hits like a dead end, like something where we're done with the constraint, where there are constraints that just simply cannot be satisfied in any circumstances, it goes backwards and it keeps going backwards. Sort of, it's kind of like that for search.
Exactly. So the tree that we're building, first of all, is assignment of values to variables. Okay. When you assign a value to a variable, sometimes the other variables are affected, which are having a constraint with this variable. In that case, their domain is shortened or lessened in some way. If at some point you find that some variable's domain is empty or some variable has no valid assignment left, you have found a dead end, and you backtrack to the point where you still have a feasible assignment for that variable. And then from there, you choose an alternative assignment for that particular node, and then keep finding till you find an actual solution. If you have found all the possible assignments and all of them have dead ends, then basically there is no solution for the given constraint satisfaction problem. OK, that is backtracking search. There were 3 heuristics that the professor or we have thought about when it comes to backtracking search. Does anyone want to attempt what those were? OK.
There's minimum remaining value.
OK, what does that entail?
So you basically check, you eliminate like values that a variable can be.
OK.
And then you just try to, I guess, enforce a consistency check on the variable with the least remaining amount of things it can.
Exactly. So we're choosing, so this gives us an idea about which variable to choose first. Again, the tree that we are building is an assignment of values to variables, right? So at each node, we are assigning one value to one variable. What we're trying to optimize here is, can we make an efficient choice about which variable we choose? And can we make an efficient choice about which value we choose? So the first heuristic is the minimum remaining values for a variable check. Once you have done that, you sometimes might get ties, where 2 variables have, let's say, domain 1. In that case, what do you do? The second heuristic. That's the second heuristic, guys. Anyone? Go ahead. Yeah, these constraining values. What does that mean?
You only pick the value that constrain the rest of the graph less, so that later on we have more spaces.
OK, that is correct. But that basically is giving you a value to pick. We are still choosing a variable. We have a tie between 2 variables. That is the third heuristic. Can someone remember the second one? OK, if you have 2 variables which have the same amount, the same domain size, the thing you check is their degree. How many constraints are they participating in? You choose the variables with the most constraint first so that you can shorten your search space. The three heuristics then, again, I'm repeating for consistency, is the minimum remaining values, the degree constraint, and the least constraining values. The first two are for choosing the variable, and the last one is for choosing the value. Okay? All these are in the slides again. If you want to review, if you have questions, come back. The utility for each, I'm pretty sure, is evident now. Okay. Now, there were two other enhancements that we talked about. First was forward checking. So forward checking has the idea of keeping track of the remaining values, legal values for unassigned variables, and we terminate the search when any variable has no legal values. So essentially, when you assign a value to the variable, a particular variable, we saw that it affects all the other variables that it is in constraints with, right? And at some point, one of these unassigned variables might have an empty domain. At that point, we stop searching. That is what forward searching means. Otherwise, what a dumb algorithm would do is basically it would start variable 1, value 1, then it'll go variable 2, value 2, and it'll forget about all the constraints that exist. But now what we're doing is, after assignment of each value, we're saying, hey, after this, what are my domains looking like? And if my domains are empty, these are for the unassigned ones, by the way. These values haven't been assigned to any of the variables yet. If any of those domains are empty, I do not search beyond this. Okay? That's a heuristic. The second one was about constraint propagation. Now here, we have propagated information from an assigned value to an assigned variable to an unassigned variable. All right? What we want to do now is see if there is any heuristic that we can build to propagate information from unassigned variables to unassigned variables. Because sometimes, let's say this variable 1 affected some variable 3. Now variable 3 has x in its domain. But variable 3 has a constraint with variable 4, and variable 4 only had x, but now doesn't have anything else left, because this only has x. So at that point, we still want to stop. This is propagation of information between unassigned variables. This is our consistency. This is constraint propagation. The first one was propagation of information between assigned and unassigned variables. This was just forward checking. Okay? So yeah, the second heuristic is arc consistency. Definition of arc consistency. Anyone want to try? If there's an arc x to y, it is consistent. Then go ahead.
For every value x, there exists a proper value y.
Yeah, exactly. For every value x of x, there is some legal y in y, essentially. Cool. There was 2 consistency, 3 consistency, k consistency. The example that, or the definition we talked about was the example of 2 consistency. We can have the similar thing for k consistency, meaning for k variables. If I have some valid assignment for k minus 1 variables, is there some possible solution for the kth variable? That's what it talks about. Again, all of these are heuristics. They will not affect your complexity. And that's what we want to remember. Perfect. But something that will affect the complexity is the structure. Again, these AI researchers, these theorists kind of want to play along different structures and find, hey, this is a more optimal solution for this particular structure. That's why they came up with something called the tree-structured CSPs. If, instead of a graph that you draw for a constraint graph, I think everyone knows, that's why I didn't go with the definition. But if your constraint graph, instead of a graph, is a tree, basically it has no backward loops, what you could do is you can solve it in nd squared time. Meaning you can order it in a certain fashion, which is topologically sorted. Topologically meaning if there's a tree, you go from high to low. That's the height. That's why topological. So you sort it in any fashion which resembles a tree. So from left to right, you should have high to low, meaning anything that is a predecessor should be a parent in the tree of the successor. If you have such nodes, then you do two passes. One is a backward pass, and then we do a forward pass. And after that, we can basically check the assignment of values. In these passes, the backward pass is basically an arc consistency check between two particular nodes. And if there are no possible values for a particular node, then we stop and we say, hey, there's no possible assignments for this particular constraint satisfaction problem. If there are values remaining in domains after you're done your backward pass, you just do the assignments of those values in the forward pass, and you should be good. An example, a short example that I will show is basically if you have A, B, C, and D, where B is the parent of D as well. You start with, let's say, the domain of D is red, the domain of C is red, yellow, the domain of B is red, yellow, green, and this is red, yellow, green, blue. So since this is only red, its parent cannot be red. So we remove red from the parent. If this is red and yellow, for each of these values, there's a possible value here, so we're good. For yellow, green, there's more possible values here, so we're good. So that is our backward pass. And then for the forward pass, we just do assignment of values. So let's say this is red, this is yellow, this is red, this is red. Okay? So that is how this algorithm works. If you have more questions, we can talk about this after this review seminar, but that is it. There's something called cut set conditioning that we went over. That was a way to convert a graph into a tree. Does anyone remember what that was? Go ahead.
You remove cycles from the graph by assigning values to that node and then treating the rest of it like a tree and then iterating over different values of that cut set.
Perfect, exactly. So if, let's say, you had a graph which was A is at the center, and there's B, there's C, there's D, there's E, and A is basically connected to all of them. What we will do, and A has domain red, yellow, green. This is, the domains are from the map coloring problem again. I'm assuming you guys know about that. What we will do here is essentially assign the value red first, and we remove all of these constraints. Okay? After, we remove red from each of their domains. So this is yellow, blue. This is yellow, blue. Yada, yada, yada. Okay? If we don't find a valid solution with this, we then assign yellow to A, and then remove yellow from these domains, add red back, and then do the same constraint satisfaction problem. The same thing again with green. Okay? So such a method will yield a better time complexity than a graph. But this is, of course, multiple iterations of a tree structured CSP. So what is the complexity here? Since we are doing the domain-sized iterations of the tree structured CSP, we are doing, let's say, the domain of A is D times nd squared. Sorry, n minus 1d squared, because now we have one less variable to assign. Okay, that's horrible handwriting. I'm sorry about that. But if, let's say, instead of A, you removed multiple nodes, you removed A and B and C and D, this formula just turns to d to the power c, n minus c, d squared. Okay, n minus c, d squared is your tree structured CSP. The number of times you do it is the domain of c variables that you removed. Okay, and that's why n minus c. That many less variables you have. Perfect. So that is your tree structured CSP. The last part in this is local search. This was also the same tutorial, same idea, hill climbing. We explored a little bit more enhancements in that, but all of those are not covered in your final. So only thing you need to know is the local search hill climbing algorithm. We assign values to all variables, and then we find if there are some inconsistencies in the constraints. We choose a constraint, we choose the variable which has an inconsistent constraint and assign a different value to it. And like that, we keep finding if there's a possible solution. The heuristic in this could be that you choose the variable with the maximum number of, choose the variable randomly and choose the value that violates the fewest number of constraints so that you have a closer idea to a optimal solution. If a value is kind of adding to the number of constraints you have, you're making your solution suboptimal and your local search is going the other way. Cool. So that is it about constraint satisfaction problems. Any questions about this? OK. Cool. Adversarial games. A deterministic game consists of states, players, actions, and transition function, terminal test, terminal utility function, whatever. But what we want to keep in mind here, there's 2 players in this case that we are discussing now. There could be multiplayers as well. A zero-sum game is what we need to think of. A zero-sum game is basically the idea that all the agents have opposite or adversarial tendencies, and the utility, because one tries to minimize and one tries to maximize, is at the end could be 0. Okay. Yes, you have a question. Oh, sorry. Oh, so this question is about converting this to a tree-structured CSP. Anyone want to talk about it? Go ahead.
Do essay first?
Yeah, do essay first. OK. OK. Cool. I'll come to this. So there is a zero-sum game. Great. What is the value of a state? Or value of a state for an agent? Any idea? Go ahead. Exactly. The reward you can get or achievable outcome, utility, whatever. That's the value of the state. OK, I'm sorry. You might have to share with your friends. OK, you're just getting too many chocolates. What is the node's minimax value then? It's the best achievable utility against a rational adversary. OK, where one agent is trying to minimize a value, one agent is trying to maximize a value. Cool. The idea of a minimax algorithm is basically we're trying to maximize the value. One player is trying to maximize the value, and one player is trying to minimize the value. We have a single utility function or single utility value. And we build a state space search tree where each level represents one adversary's turn. Okay? So after each turn, an agent can choose to perform different actions. We're trying to kind of capture that in our state space search tree. Perfect. In this, there was a way to kind of improve your improve your ability to find enhance your ability to find the solution faster. That was using alpha-beta pruning. Anyone want to give a try of why alpha-beta pruning works? What it is? What do we do? Go ahead.
So basically, it sort of removes unnecessary nodes, which can end up saving a lot of time.
OK. Essentially. The idea between that, when do we basically prune the nodes? Any idea?
So let's say we have you have like a maximization node, right?
Uh-huh.
And then you find, and then the node, and then its leaves are minimization.
Okay.
So if you find something inside like the leaves, if you find something inside their children that's less than the current like maximized value,
Yep.
then you can just get rid of that node entirely because under like if your opponent plays optimally, that means that they will never under any circumstance choose a specific node.
Yep.
So you can just get rid of that one entirely.
Exactly. So again, if you are a max agent and your children are minimum agents, so essentially I'm talking about a tree, okay? So you are a max node and you have children as min nodes. You found a certain value for a min node which was higher than all the second one or the third one, whatever their children are. You don't need to worry about the children below the min node, which are going to give you lesser values. If the second min node gave a value which is less than the first min node already, then we know we are not going to get that value. So you don't need to search that and you can prune it. That's what we are doing as an optimization for this. What this is an amazing website that some people developed, which allows you to generate a tree, shows you a solution of how alpha-beta pruning will be executed on it. It has fantastic animations, and it has plenty of examples in practice. I personally did everything from here when I was taking the course. I think this is going to be much better than me explaining it here, because that's going to take a lot of time too. So I think everyone can just scan this. And if you want to see a demonstration, you can meet me after the review seminar. I can show it to you as well. Does anyone still want to see like how alpha-beta pruning works? Or is everyone confident about it? Also, it's very unlikely you'll get a question about that. I'm sorry. It's very unlikely you'll get a question about that in your final because you already got it in the midterm. And there's much more important topics to cover in the final. OK, cool. So minimax, alpha-beta pruning, great, everything is done. The generalization of such an adversarial game could be where we have multiple agents and a non-zero-sum game where someone is trying to minimize, someone is trying to maximize, et cetera, and it does not add up to 0. In such a case, we have terminal nodes as tuples of different values that an agent can have. Each player tries to maximize its own component from that tuple in every turn. This can give rise to cooperation. Basically, it's like a Monopoly game where two people can now, hey, if we together own the railroads, we are going to be the kings or whatever. So that minimization or maximization function can now occur with two particular agents acting at once in a cooperative fashion. Cool. And then there was like a probabilistic approach to this where you don't know if the outcomes are certain or not. So there was expect Tmax or expect Minimax. You essentially calculate the expected outcome or expected utility that you can get from a particular node and then take your decision. Cool. There was one more part in this which we covered in tutorials. In a way, I kind of went over it very quickly because I thought it was not very important. It does not belong in an AI course. But the prof thinks it's important, and we're going to kind of study it today again. This was about game theory. Okay? This was Nash equilibrium that we saw the pure strategy for. But for this, I'm going to, again, share. OK, this sheet, which I have, is basically the gift that you're going to get at the end. The sheet has a lot of definitions written down, most of the definitions that are needed written down one by one. I think it is important for us to understand some basic definitions in game theory before we start approaching problems in it. Okay? So one simple understanding. What is a game? What is a strategic game? Okay, a strategic game consists of a set of players, a set of actions for those players, and the preferences that the players have over those actions. Okay? These preferences are ordinal. They want to maximize their chance of winning, ideally. But it could change in the case where I don't know what my adversary is playing with. Okay? So that's why they have certain preference profiles in a strategic game. In this case, we're assuming ordinal preferences, meaning I will play in my best interest. I'm not giving away the game to my adversary. Okay? A strategy is the probability with which a player chooses to perform each action. Okay? So if I have 8 actions to my, at my disposal, the probability with which I perform each is my strategy. Okay? So on the board that day, we drew some actions. Agent 1, left, right, or dove hawk, left, right. So these are both actions. The probability with which I perform these actions is my strategy. Okay? A dominant strategy. A dominant strategy is a strategy that always wins. Basically, it is always better for me to play that particular action irrespective of what my other player plays. A dominated strategy is basically a strategy in which I always lose. So basically, the other action of the dominant strategy would be the dominated strategy. A pure strategy is where I have 100% probability to play one action. Okay? So in case of dominant strategies, I will always play that action. So that is a pure strategy. A mixed strategy is where I will play one action with certain probability and the other action with 1 minus that probability. Here I'm assuming there are 2 actions only because that's enough complication. But essentially the division of probabilities is called a mixed strategy. A Nash equilibrium. A Nash equilibrium is a state or, okay, let's go precise. An outcome is a Nash equilibrium. An outcome meaning some agents took actions, and from those actions, they got some rewards. So those rewards are outcomes of their actions, and that outcome is a Nash equilibrium. If player A's action is an optimal response to player B's action, and vice versa, player B's action is an optimal response to player A's action. Another way that we frame this during tutorial so that we can use this in practice better is that it is a set of strategies, one for each player. So here, before it was like an outcome thing, now it is a set of strategies. Like those outcomes come from strategies, right? So a Nash equilibrium is a set of strategies, one for each player, such that no player has an incentive to deviate unilaterally, meaning the other player is not deviating. In that case, if I deviate, I am always at a loss, or I perform worse, or I get less outcomes, all right? That is what a Nash equilibrium is. A mixed Nash equilibrium, on the other hand, is where a player will choose a probability such that any action so a player can choose a probability about its actions, okay? If I assign certain probabilities to certain actions, what it means is, so mixed Nash equilibrium means is, for player 2, performing any action is indifferent, because the outcome that I will get is always, so the expected outcome that I will get is always the same. So a mixed Nash equilibrium exists if certain probabilities exist such that I get an expected payoff which is always equal in all the cases, all right? There's an example, the same example from tutorial in the final exam, so we will go over that again and I'll explain this better, I think. But that is it. Okay, so that was game theory. Last topic that I will cover is Markov decision processes. I think we went over this very, very in detail in the tutorial, but if you have any questions, I'm here to answer them. Essentially, a Markov decision process consists of set of states, set of actions, start state or initial state, transition function, reward function, and discounts. Okay, what we are trying to do is achieve a goal, and each state has a reward based on that proximity to goal or whatever we're trying to achieve there. A thing that is in Prof's slides about what you should know for the exam is Markovian transitions, which I had to even revise because it was on his slides. A Markovian transition is a transition when the action outcomes depend only on the current state. So essentially, the outcome of my current action only depends on my current state, not any previous states. That's a Markovian transition. A state is an assignment to the state variables. A Q state, which is also in his things to know, is a state paired with an action that can be taken in that state. Okay? So the Q values that we were assigning to QSA basically is a Q state. State on its own is the VS, the S part. Okay. What is the role of a discount factor? This is also something you should know. We want to provide, oh, go ahead.
Next slide, it should be next slide.
Oh. Sure. This is the example from the tutorial. If you want me to go over it again, I can, but I genuinely went through it with a lot of effort. Okay. So I was going at the role of a discount factor. The role of a discount factor, again, back then I told you it was to get money today is better than money tomorrow, right? It was to get the reward as early as possible, reach the goal as early as possible, in the fewest number of states, actions as possible. Another way to frame it is we want to keep the total reward finite, but we want to reach to the reward as soon as possible. So that is why we have, so if you remember the summation that we had for a discount factor was an AGM, geometric harmonic series, which was gamma squared, gamma cubed times the reward you get at each state. So if you want to keep that series finite, you need to have a constant which is less than 1, which is being multiplied every time. Otherwise, your gamma to the power something is going to keep increasing forever, right? Okay, so that is your discount factor. What is the value of a state under policy? It's the maximum Q value you can get from taking actions in that state. Or you can also define it using the formula, which, if you see, the formula is complicated, which I think I wasn't able to remember at first. It was like too convoluted. But if you try to understand what it means, it gives you better intuition. So the formula is, I think I can write on this, right? It's right here. Okay. So the value of a state is the max over all actions, the sum of TSAS prime. Can someone remember what is TSAS prime? It's a transition function, right? Transition probability, yes, exactly. And RSAS prime, what was that? Rewards, exactly. Gamma is the discount factor, and Vk is the value of the state S prime, right? So this is the expected amount of reward or outcome or utility that I can get at this state, okay? That's why this is the probability times the value summed, okay? That's the expected reward or value I can get at this state. The procedure, sorry, go ahead.
It has a k plus 1 k. Is that just like
Yeah, this was the recursive version of Bellman equations. It can also be like V pi star, and then this is just V pi a. Cool. Okay, so also if, let's say this was defined in terms of Q, as you were saying, instead of the recursive definition, the value of S at, so the value of S at policy pi is going to be maximum of A belonging to A, the Q pi SA, right? So it's the quality or Q value that you can get from taking action A at state S, according to the policy pi, all right? This was the recursive definition for finding a new value for this one. Okay, the idea of value iteration then is you start with the initial state where all the values are 0 because you have not had any progress. There's no time steps. And so the expected reward sum is of 0. Anyway, given a vector VKS values, do one ply of expectee max for each state. So we're trying to do the maximum expectation you can get for each state, and then repeat this until convergence. So the idea here that was given by Markov, which was mind-blowing, was this state or this series of values will converge at some point once you keep doing this iteratively, all right? The time complexity for this algorithm was S squared A, O of S squared A, where S is the size of the state space and A is the size of the actions. Cool. There's two more things about policy evaluation, policy extraction that you need to know. It's nothing crazy. It's just argmax of A. So once you know the optimal values, how can you extract the policy? Any idea? Yeah, exactly. So you get the action, which will maximize the Q value. The policy is a set of actions given a state, right? So the policy star at state S is the argmax of A over this function. Perfect. Okay, and that brings us to the end of part 1 of this course. Any questions in anything that I've talked about till now? Okay, let's take a 5-minute break, and then we'll transition over to the second part. And we're good.
I'm just winging it. Oh no, I have some things written out. Before I begin, there's two options. So we started a little bit late, and we want to make sure that we're pretty thorough in the way we explain things. So you have 3 options right now. One is continue learning post-midterm stuff, which will approximately take us to 5, and then you guys can go home and do the practice sample final, which I really suggest that option, because just going over, just watching me do them might not give you the experience that you need. Option 2, we just stay longer. right? And option 3, I skip the post-midterm recap and we straight up do the sample final. Okay, I'm going to take a poll. Option 1, do the summary, finish the summary, go home. Option 2, finish the summary and do the final. Okay, cool. Don't need option number 3. Okay, we're going to start with post-midterm. The first thing you learned was reinforcement learning. My question to you is, what's the whole point? What do we do MDP for? What are we doing reinforcement learning for? What are we trying to do? There's supposed to be some, we're not doing this for fun. This wasn't made just for D84 for you to get a 4.0 and for me to show up on Saturday here to do this review seminar. There's some reason we want it. Why do we want it? Yes?
Because you may not have all the information for the MVP, like the transition and the rewards. So you want to learn it.
What's the whole point of any of it? Of MDP as well? What's the whole point? What are we trying to learn?
Trying to maximize your utility as an agent in a world where you
By doing what? What are we trying to find? Given a state, we're finding an action. We're finding a policy. That's the whole point of this entire exercise. For some state, we want to find, we're trying to find what the best action is for that state. That's the only thing that the agent can control, and the agent is trying to maximize some sort of reward, right? So that's our goal. We've seen the MDP model, which requires transitions and to know the rewards beforehand. But in real-world scenarios, we usually don't have those. So can we get away without knowing them? That's the goal, right? How do we get away without them? We still need to somehow figure out the policy, right? So we still need either V or Q. We need the value table, we need the Q table somehow. But can we get away without knowing the rewards beforehand, without knowing the rewards, the transition probabilities beforehand? So the first thing, the best thing, or the easiest thing that some genius came up with was like, okay, let me just start. Let me have some random policy. Let me start with a completely random policy, and let me just run a bunch of times until I run it at this state, and it just runs, and then it terminated after some number of moves. And then, so this is a single run, right? This is a single sample run. An episode is a set of sample runs, right? So let's say I do a single run of Pac-Man, and then, ghost caught Pac-Man, done. Another run, somehow randomly it ate everything, it won, blah, 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 blah. You do 100 of those, and you have this data. Now you can work backwards to figure out the rewards, right? So for a particular sample run, if the sample run was 50 steps, then there were 50 states, right? For each state, you ended at a particular state, and you then at that point you can compute the reward, right, at the final state. So then you can sort of propagate that reward backwards to figure out the value, the discounted value of this state, the discounted reward of this particular state in this particular sample run. So then what do? We just average over all the sample runs in an episode. And that will give us a good estimate of the value of the state, right? So that's direct evaluation, right? Step 1, you take a sample. How do you take a sample? You start at some state, and then you actually use the policy. If you don't have a policy beforehand, it's the random policy, right? So use policy pi. Okay, step number 2, compute for each state S in some sample run, let's say sample run I, you compute the discounted reward. Right? That sample run has to have ended. It has to end in some finite number of steps. And then after that, you compute the discounted reward. And then you store it for that state for that particular run, right? Step number 3, you do this for every state and sample run. And finally, you aggregate over the state. Well, you aggregate over the runs for each state. So for each state, aggregate over all sample runs. Okay. Yes. You sure that's not my mouth? Is this better? Sure, I can take it off. Okay, so where were we? Yes, so you do this. So if in a particular episode there's 100 sample runs, but a state only occurs in 10 of those sample runs, then you only have to average those 10 values, right, for that state. And then you have an approximation of your V. Okay, cool. There's a problem with this. What's the problem? When do we update the policy? Sure. Step 4 is update policy, by the way. When do we update the policy? At the very end, which means you have to do the entire episode, every state, take all the averages. And up until then, if you have a shitty policy, you're just working with a shitty policy, right? We want our updates to be a little bit more minute and a little bit more instant, right? So the problem is you have to wait for every episode to end to update the policy. How do we fix this? In comes temporal difference learning, okay? Does everyone understand why there's a problem here? And now I'll explain why temporal differences will help fix it. Okay. So in temporal differences, instead of waiting up until the end of the policy, we end up taking a running average. So we update immediately, right? So this is how the temporal difference works. The value of the policy is the old value times some 1 minus alpha plus the sample, which is the new sort of value that we just got in this current run, times alpha. So this 1 minus alpha and alpha, where alpha is between 0 and 1, is just a weighted average, right? It's just a weighted average of the old value and the new value. This is the learning rate. The sample is nothing but the value of what we just observed, right? So it's the reward, the immediate reward of going from state A using some action. What's the action actually here? Policy. Good. Using the policy. And let's say it ended us in S prime. So that's the immediate reward plus the discounted reward of whatever the value is of this new state, right? And that's your sample. And you would make this update every single time. Every time you take an action in any sample run, you go to the next step, you get this value, plus you get this value based off of your current value table. You plug it in, you update, right? So this is immediate updates as opposed to batch updates that happen in direct learning, in direct evaluation. Okay, what does this do? It sort of makes v pi s consistent with v pi s prime, right? Bit by bit. So it inches v pi s to v pi s prime, right? So it improves consistency between neighboring states. If your learning rate was 1, it just means we're just going to take the new sample and completely disregard all the previous runs, which is kind of stupid. So you want to usually keep the learning rate far away from 1. Cool? Oh. All right. Before I say what's wrong with this, any questions? No questions? Cool. All right. So this helps us compute the values of a state. What's the problem here? Yes?
It's hard to go from values to the optimal policy.
Exactly. We have the values, but we don't have the corresponding action that got us those optimal values, right? This is a problem. We lost track. We were just like, okay, yeah, we don't need this. We can just get the V's, and then, oh, whoops, we forgot the actions. So what do we need? We don't need the values. We need the Q table. We need the QSA pairs, right? From that, we can compute the policy by taking the argmax, right? The best way I like to represent it as is as the following. Let's say you have whatever 10 actions, A1 through A10, and then you have a bunch of states, state 1 to state n. This is your Q table. The best action in this Q table, what is Q of S1 A1? It's the value of taking action 1 in state 1, right? So to find the best action, I just have to take the max of this row. That's all I have to do. That's how I'm finding the policy. I look at this, and I take not the max value, we want the action. So you find the max, and you take the corresponding action, whatever column it is, and that's your policy, right? So this is what we want. We don't have the Q table in TD learning, so we need to find a way to get the Q table. Okay, so we want this. Well, where pi star is the optimum policy, and we want to approximate it somehow, right? Cool. Now, okay, I'm going to skip. There's some things about exploration and exploitation. I'm going to skip it. I'm going to continue finishing this, and then we'll go back to exploration and exploitation. Okay. So, well, I guess I skipped this formula. I would need that sheet wherever it is. Oh, I do have it. There we go. Cool. So, instead, just like we were doing this update, this sort of weighted update of the value table, we can do the same thing with the Q table, right? But this time, instead of just distinguishing between the state and state prime, we now take into account the action that got us there, right? So it's literally temporal difference, but with the additional split that we're actually keeping the actions a little bit separate so that we can actually compute the Q table at the end. So then the same update would occur. You would get this weighted average, 1 minus alpha times whatever it already was, plus alpha times the sample. Or the sample is the exact same thing. The sample is the immediate reward of going from state A with action A to S prime, plus the discounted reward given by the Q table. Well, actually, this would still be the value, but we don't have the V anymore. So what do? This would still be the value according to pi star of S. We don't have V. But what is V? Yes?
The sum over all the QAs, or the average.
Yeah, did I remove the, okay. I'm going to draw the thing again. S1 to Sn, A1 to AK. If I want to find the value of a particular state, what do? Yes? You find the maximum value here, and that's the value of the state. And what is the policy for that particular state? Just the column, just the action, right? So just giving you, let's say for state I, action J is the one that maximizes it. Whatever Q value is here is your value. of that state, v pi si, is q of si comma aj. And whatever the corresponding aj is your policy, right? So this is your pi of si. So then the value is nothing but the best thing in the row, which is the max over all the possible things in the row, which is max over a prime, q, s prime, a prime. There we go. Now you have the formula for Q learning. Cool. Questions? Any questions? No? Now we have the Q table. It's an identical approximation. It will converge. We're not going to talk about the proof of why it converges. But it will converge. And therefore, this is it. Now you can find the policy because you have the state action pairs. That's it. We're done with Q learning. I want to go back to the thing that I skipped very quickly and talk a little bit about what exploration is and what exploitation is. And it doesn't have to do too much regarding MDPs or this. But in a state space, you either have you have a current policy, and you have two options. Either I go explore some new nodes, or I stick to my current policy, right? So exploration is going out, trying something else that might not be good. You might not like it. It's going out and trying some new cuisine, for example, right? And there's a small probability that you might love that cuisine. So there's a great reward if you end up discovering it and liking it. Versus sticking to what you usually like, Subway and whatever, Taco Bell, which has its own benefits, which is, life is consistent. You don't have to think too much. You go out, you're always eating Subway. You don't have to think. What we want to do is we want a little bit of both, right? You want to be able to explore, but also know that, hey, I'm exploring too much. I need some consistency in life. So the workaround for this is to sort of flip a coin. I flip a coin. If it's heads, I go explore something new. If it's tails, I do what I usually do, right? That sort of accounts for ending up giving you a good mix of things, right? Now, it doesn't have to be a 50-50 split. It could be whatever, an epsilon and 1 minus epsilon split. The important thing is, regardless of what epsilon is, even if there's a very 0.001% chance that you will go explore, when you take the limit over everything, if you explore long enough, you will still end up covering every state infinitely many times, and you would still converge, right? Cool. But if I set my exploration to be 0.5, and then at some point I've explored enough and I've learned enough, and I've updated my policy enough, do I still need to keep exploring at a 50% chance? I don't, right? So what's the trick? I start out exploring a lot, and then soon, once I've explored a bunch of things, I can explore less and less, right? So it's called epsilon decay. It's where you dynamically reduce how much you explore once you have built a bunch of, you've taken a bunch of samples and you've built a policy, right? Cool. So that's epsilon decay. There's just this word, regret. Regret is the cost of exploration, right? It's how much reward you sort of lost by not sticking to your optimal current policy, right? Because not all exploration is good. You might end up disliking things as well, right? We want to minimize regret, but that means you want to optimize learning. Not only learn the optimal, but learn the optimal optimally, which is its own thing, right? That's why we're not talking about it. OK, that's it for reinforcement learning. Questions? No questions. Good. Wait, does that mean I'm going too fast? No, I'm good? And everyone's understanding? Good. Yes?
One quick question. So we're not going to discuss how to minimize regret?
No, not really. There's a diagram there if you want. Fixed epsilon versus greedy. Yeah.
Would we be expected, on the final, to calculate the regret?
No. Don't bother. It's fine. Cool. All right. Next up, we have BayesNet. This is something I covered in the tutorial, so, well, not the entirety of it. I did end up covering D-separation. We'll go over that in a bit. But before we do that, there's a couple prerequisites that are essential for you to know. And this is, first of all, this is conditional probability chaining. Right? This is just from B52. And this is what will help us break this joint probability into simpler conditional probabilities. Right? There's some important probability properties of Bayesian network Bayesian models that allow us to do this. Okay? I'm going to write something here, which I'll refer to later. Okay. I'm actually going to get this out of the way too. If you were to have the, let's say each variable has a domain size of d, right? Then if you wanted to make this massive joint probability table, what would its size be? It would be d to the power n, right? And I'm saying Bayesian networks bring this down to going from something that's exponential to something that's linear in n, given some constant k. So if I have ensured that my Bayesian network is sparse in the sense that it doesn't have a lot of parents, right? The maximum number of parents is some k, where k is much, much smaller than n. Then I have greatly improved my runtime, right? Or the things I need to store. Even space complexity-wise, I will need to store a lot less, right? OK, so what is your Bayesian model? It's two things. It's a directed acyclic graph, right? And it is a set of conditional probability tables. For every single node over here, let's give them names. For every single node over here, it will have a corresponding conditional probability table, right? And this just represents the dependencies, right? So A doesn't depend on anything. So its probability table isn't conditional at all, right? Its probability table just is A is either true or false or whatever its domain is. B doesn't have its own probability table. It has a probability table that depends on A. So you have a probability table for B given A, right? And then similarly, D given A, C given B, E given B and D, right? So this E has two parents. OK, so you have these conditional probability tables. If I were to topologically sort these five things, what does it mean to topologically sort in a directed acyclic graph? Anyone? Yes?
Deal with the topmost parent first and then the order?
Yes. In a more general sense, it means a sequence of the nodes, a sequence of V, such that, yes?
It is sorted by in degree, like how many in degrees a node has.
Not exactly. You just need to enforce that for any node that appears in the sequence, all its parents, all its edges come before in the sequence, right? So one such topological sort would be A, B, C, D, and E. Another one would be A, B, D, C, E. still works the same way. Okay? So this is some topological sort. And why is this important? Because when we break this using this conditional probability table, we'll be using the fact that B given A is independent of everything else, right? So, okay, I might have to take a little little detour to talk about D-separation to show what it means to actually be conditionally independent in this graph, right? But if I were to show this graph should help you understand that B, if I have A, I don't need anything else, so B is independent of everything else given A, right? I will show this using D-separation. Well, we proved it in class, but over here I'll just list it out. And then once that's done, we'll see why writing it out like this helps us. Okay. Okay, D-separation. So x comma y are variables in some Bayesian network. They are conditionally independent given some evidence E. Everyone comfortable with what it means to be what evidence means? It's just a set of variables that are known, that whose value or whose assignment we can observe or we have observed, right? Okay. If and only if for every path between x and y, every undirected path, notice I don't have an arrow on either side. For every undirected path between x and y, there is some z on the path such that, let me erase this, such that one of these three cases holds. Z is in the evidence and you have this case. What is this case? This case is where, well, we're looking at undirected paths, but there's actual direction. And we're saying if Z has one incoming and one outgoing edge, regardless of which way it's going, and it's in the evidence, then there's independence, right? What does this mean? Okay, X has some sort of influence on Y, right? If it's going in this direction. But if I have Z, I can forego of X. I don't need X. I have Z, which is even closer. So I don't need X to figure out what Y is. I already have Z along this particular path, right? So that's what it means. 2, you have some Z in the evidence such that, or and, Z has outgoing edges that end up going to X. And an outgoing edge that ends up going to Y, right? Now, why does this show independence? Well, okay, so there is some path, so there's some dependence between X and Y, but they're both emanating from Z. So if I have Z, I don't need Y anymore, right? I can forego of Y to figure out what X is. Does that make sense? Again, this is your second case. I'm going to make it level so I have space for my third case. Okay, My third case is a little tricky. Well, that's not my third case. Deseparation's third case is a little tricky. In these, it made sense that once you have z, it sort of cuts the path off, and you can use z to figure out y instead of waiting for x, or instead of needing x. In this case, we don't want z in the evidence, and we don't want any of its descendants in the evidence either. And we want this sort of relationship. What does two incoming edges mean? What does this mean? Z is influenced by both x and y, right? That's what this means. So if I had some information about z, right, I can somehow figure out the relationship that x and y have, right? If I have some information about z, I can then work backwards for x and work backwards for y. And they're both dependent on just this value of z. Therefore, what happens? If I have z, I can work out both x and y. So they're dependent. What's the correlation between them? What's common between them? This z node. OK, so that's OK. Then it makes sense. Then I don't want z in my evidence. But why the descendants? Why do we not want the descendants? Yes.
Because if you have the descendant in evidence, you can work back up to z.
Exactly. Exactly. If we don't want z, but if we have a descendant, we could work our way back using that descendant to infer something about z. And then we're back to square one. Now we know something about z, and now we know something about x and y, and they're related. So not only do we not need z, we don't need any of its descendant. Cool? These are the three conditions. Questions? No questions. Lovely. OK, so what was the topological sort that I wrote? Did anyone write it down? A, B, C, D, E? Wait, did I actually do that? Yeah, that's cool. Nice. OK, let's move this up. And let's see, using our rules of independence. Notice that all of these actually only follow rule 1. Right? This is a very easy case to show that everything's independent. But if we were to use that, what would happen? Probability of A, B, C, D, E. A, B, C, D, E is the probability of A, probability of B given A, probability of C given A and B, probability of D given ABC, and then finally the probability of E given A, B, C, D. I've done nothing but use the expansion, right? The chain rule. OK, what does the independence allow us to do here now? Yes?
We could just take A, B, probability of A, probability of B, probability of C, probability of D, and probability of E.
Not exactly.
Well, you can just like strip off A at least.
For probability C given A, B, you can spin it out to just C given B.
Right, because C given B is independent of everything else. So we don't need A here. Right? And then the same thing. D given A is independent of B and C. And then E given D is independent of everything else.
Would it still be dependent on B?
What would, oh, whoops, sure. Correct. Right? Now, this table we have, the conditional probability table, this we have, this we have, this we have. We have all the conditional probability tables. Great. Right? This allows us to reduce a massive joint probability distribution into just like 5 separate tiny conditional probability tables. OK. So let's say I have some query I need to figure out based on the Bayes model and the conditional probability table. You know, what's the probability that blah, blah, blah happens given that I've seen blah, 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 right? So what's the probability of a query given some evidence E, right? Let's say I want that. Probability of Q given E. There's two kinds of inference for this. One is direct, and one is approximate. Well, not direct, exact, right? So let's start with exact inference. And then what else do I have? Okay, I have approximate after. And then we can take a small break, actually. We have time for that. Can I erase this? Yes? Okay. Okay, so to compute this conditional, we first need to compute the joint, right? If we have the joint, we can find the conditional afterwards by only looking at the relevant rows or columns based off of the evidence, right? So Q comma E. In fact, there's a relationship between these two. Does anyone know the relationship between these two? Recall B52. Recall A67, actually. Okay, what does it mean to normalize, though? What's the exact relationship between the two?
Multiplied by B.
Yeah. Right? This is whatever. What's it called? Bayes rule or something?
Total probability, loss of probability.
Oh, it's just the probability of this E. Okay, so this, as you said, does end up making the sort of 1 over this ends up making your normalization constant, right? In fact, you'd have to normalize for every single one of these, conditional probabilities if you ever need to. But you know that at the end it's just normalization, so you can just clump them all together and abstract that away, right? But it does have an inherent meaning. I think I talked a little bit about what the actual, alpha 1, 2, 3 mean when I do the hidden Markov models in the video walkthrough of the solution. So if you want some insight, you can go there. Okay. So option number 1 is enumeration. It says, build this giant joint probability table, right? So build this massive joint probability table for everything, right? And then eliminate away all the variables, the hidden variables. What are the hidden variables in this scenario? What do I mean by hidden variables? Whatever's not in the query or the evidence, right? Those are things I don't need. So if we have a table, if we have this entire joint probability table, I don't really need exact values for those, so I can abstract that away by summing all of them up, right? So build this giant probability table, and then sum out or eliminate the hidden variables. The probability table exponentially grows, right? It grows exponentially if I increase, if I add one more variable, right? If my Bayesian network has one more variable, this table it doubles in size, right? Okay. So that's the problem with this. The complexity is proportional to the size of the largest factor, and if we wait till the end to eliminate the hidden variables, the size of the factor will be massive, right? It would be whatever, 2 to the power n. So instead of waiting till the end, we should do something better, right? What can we do? Yes?
You interleave the joint, combining of tables and summing them out.
Yeah, yeah. And that would give you the second approach, which is variable elimination. So variable elimination don't wait till end to sum out hidden variables. Okay. So how do you actually do this? Step 1, identify the factors. What are your initial factors if you have a Bayesian network and some conditional probability tables? What are your set of initial factors?
Depends.
It doesn't depend. Yes.
You select evidence.
What are the factors?
CPT.
Exactly. Your CPTs? With what? Instantiated. With the evidence. This is always your first step, right? You don't have any other factors. So in our case, it would be all of these 5, right? Now this is just without any evidence, but if I had evidence, I would instantiate it. Instantiating an evidence just means if it's whatever. If E was 5, if I've observed it, then I don't need all the columns that correspond to E being anything else. I can remove them, right? Okay, so now I have these factors. What's the next step? Anyone? Yes? Yeah, the hidden variable, right? So pick a hidden variable. And you would join all those related factors, right? So you would have this massive, not massive, you'd have this joint probability table that contains this hidden variable, and no other factor that's out there contains this hidden variable anymore. You're done. This is the only factor after you've done joining that will actually contain the hidden variable, right? Or that's not okay. It's not a factor yet because you have to sum it out. But once the joint probability table is the only place you have that hidden variable. And your next step is to sum it out, right? Sum out hidden variable. Okay. Next step. Repeat till no hidden variables. Okay. Finally, join remaining factors. Compute query. And then normalize. Okay, so that's your last step. I realized I might have written it a little bit too low. I apologize for that. Cool. Everyone okay with this? This is the procedure, right? There's one thing where we can actually choose something. Where are we choosing in this? Yes? Right. So when it comes to choosing things, there's probably some good way to choose it, right? What's the best? What's a good heuristic?
Elimination with?
Yes. You know? Do you recall the name?
Was it not elimination?
No.
Minimum?
Minimum, it's called something. It's called the min-fill heuristic, right? What is the min-fill heuristic? You pick the hidden variable that will result in the smallest factor. Yes.
Would it be the hidden variable or the minimum?
What does it mean for a variable to be minimum? You pick the hidden variable such that when the factor that's going to arise after you join it based off of that hidden variable has the smallest size possible. What's the size of a factor? Anyone?
Capital letters in the factor.
That's not the size.
To have the evidence, for example,
Yeah.
P of EB would have a factor of 3. Sorry, not a factor, elimination width of 3.
Elimination width, yes. The size is 2 to the power 3, right? So it's the same thing. You either just look at the exponent or look at the size. You want to pick the one that's the smallest, right? So what will we do for this? Let's say we want a probability of, I don't know, D given, where's the graph? It's whatever. C equals whatever, plus C. So then my hidden variables are A, B, and E, right? So if I choose A, then when I combine it and sum out, I'm only going to get probability of B, right? So that has elimination width 1. If I choose B, then B occurs here, here, and here. So I'm going to have probably a larger elimination width, right? So min-fill heuristic will say, OK, let's eliminate A first, and then figure out between whatever, D and E, which one to pick, right? Yes?
So when we say that the size would be 2 to the 3, is that only considering if the domain is binary?
Yes.
Okay,
If it had some other domain, it would be D to the power of 3. Yeah? OK. Although there is supposed to be some sort of abstraction and generalization, you will not be asked to do anything that has like more than 2 or 3 in the domain. Okay? Even 3 is pushing it. You'll probably just have trues and falses.
If you had evidence, for example, for P given BD, if you had, for example, B and D, would that not reduce your elimination?
If you had B and D,
Yeah.
this would just become a table of 2.
Right, so then the elimination width would just be 1, no?
Yes, yes. So, OK, I might as well write this down. The factor size, or your elimination width, whatever you want to call it, factor size is 2 to the power number of uninstantiated variables in the factor. Or your elimination width would just be the number of uninstantiated. So if B and D were instantiated, the size of this factor is just 1. Or the elimination width is 1, the size is 2. Right? Cool? Great. That's it for exact inference. Great. Cool. I'm going to skip a poly tree. It is fairly straightforward. There's nothing that's different about that. One thing that you should note, variable elimination in a poly tree is linear in the size of the network, because the factor size never increases, because there's always a node that is like a single node, like P of A over there. All right? Cool. Let's move on to something that's a little bit more abstract. That's not super abstract, but in my opinion, it's a little bit harder to grasp, which is approximate inference. Yeah.
You wouldn't go through the whole, in this case, you wouldn't go through the whole algorithm. You can just combine the first two
Yeah, because if you just had P of AB, it would be it would just cut off here, right? So then you just have these two factors, right? Yeah, sure. Okay. We'll erase it when we get to it. Approximate inference. Why do we have to approximate it in the first place?
We don't know.
We don't know what?
We don't know the actual values
Okay, of what?
of like the actual conditional probability.
Okay, we don't have the CPTs, right? But we have the graph, right? Yes. We'll get to that soon, because there's a difference between being an exact solution and an approximate solution. If you've taken C73, there are some polytime approximation algorithms for things that don't have a polytime complete algorithm, right? So there's a trade-off there, and you are correct. If you do this right, most of the time, this will be faster. Okay. No CPT, but you definitely have the model, because if you don't have the model and you don't have the CPTs, you have nothing. What are you doing? But have model. So you have the directed acyclic graph. Okay. So how do we actually go about and even estimate the conditional probability tables, let alone whatever query that we're trying to find? How do we go about estimating these probabilities? Yes.
Count versus total.
Of what? Count of what?
The samples that we're looking for. So if we do
What's a sample?
So we have to take some samples of the data where we observe some configuration and then we count the observations.
Yeah, so we have to create samples, right? So that's our first step. Sampling. Everything you see afterwards is just different kinds of sampling. And in fact, they occur in a sequence in a very specific order because one has a caveat that the other one fills and the other one still has some other caveat that the third one fills and so on and so forth, right? It's the same thing as we did with TD learning and then we went to Q learning. I don't know why you guys need to know the entire history of things. You could have just learned Gibbs sampling, but it helps build intuition. Okay? So the first thing you can do is, because it's a directed acyclic graph, you will sort the variables in topological order. You will always assume whenever I write x1 through xn, they're sorted. All right? So are topo sorted. This is not a word, I'm making it up, but it makes sense. Cool. How do you actually sample? You have to sample xi from the probability of xi given the parents. Right? So first you sample x1. That is something that has no dependence. It's random. But now once you have a value of x1 based on this value, you can now query or sample x2 and so on and so forth. Right? You don't have this probability, by the way. They're estimating this. But what this means is given that you've sampled everything before, you can sample the next one. Right? In this topological sort. Cool. So you sample xi, and then you return the entire thing. And that is just one sample. That's one sample of all the values, right? And then what would you do? You would keep doing this, and you would take the average, right? And averaging will give you a good estimate. Cool. Okay. Okay, this is fine and dandy. We should just go home. But someone out there was like, what if we want to query something that has evidence, right? Because here, we're just sampling everything. And that will give us a good joint probability. It would give us a joint probability distribution of everything, right? Of all x1 through xn, so 2 to the power n. But someone was out there like, hold on. What if we just want a conditional, just a tiny query? I don't need to compute everything. This is the same problem with enumeration, right? For which we solved by variable elimination. So they were like, OK, here's an idea. While sampling, if whatever we sample doesn't match what the evidence is supposed to be in the query, we just disregard that sample. We just move on, skip, right? Or in a for loop, we just hit continue, right? So rejection. If the query is conditional, let's say it's something like the probability of C given A is 1 and whatever, B is 2, right? We don't care for the full joint probability table. And we don't care for samples where A is not 1 or B is not 1. A equals 1, 2. A equals 1 and B equals 2 redefines the scope of the probabilities that we're looking for. So we don't care about any samples that do this. So the only thing we need to change over here is an extra step, right? We just need a rejection step. If xi is evidence, then fix its value. Right? Okay. So what does this do now? It will only create samples that are consistent with the evidence, right? So now we're only looking at this subproblem. Why is this important? Why is this important? We don't care about anything else. OK, cool. Now are we happy with this? What's the problem here? Yes?
We're messing up the counts?
No, not really. Because your counts are scoped based off of these new scopes that's defined. Yes?
Wait, are we still on rejection sampling?
Yeah.
I thought when you fix the evidence, I thought that's the next one, the likelihood weighting.
The likelihood weighting is where you weight the sample with something.
Okay, well.
There's a problem with this, which will get us to likelihood.
Is it if the evidence probability is really low, will it throw out everything?
Exactly. So you run this for loop many, many, many times. And let's say the evidence was xn, right? It was the last value. So it's always the last thing that we're generating. And let's say the probability that xn is particularly that part, whatever that evidence is extremely rare. It's 0.00001. So when I do all of this, I run this massive for loop, I sample everything, and then for the last step, there's literally no chance that I'm going to get the sample that is consistent with my evidence. What ends up happening? I just waste it, right? I have to skip that for loop, essentially. So the problem with rejection sampling wait, I think I've done something wrong here. Yes. It's not then fix the value. It's reject. If xi sample inconsistent with evidence, skip. Right? So now, just to get 10 samples, if the probability of our evidence being that value is whatever, 0.01, I would need to run 1,000 samples just to get 10 that actually are consistent with the evidence, right? That's the problem here. Problem. If evidence unlikely, a lot of wasted computation. Okay. And because of this as well, it also means it'll take longer to converge. Right? What's the solution? Anyone? What fixes it? What's the next thing? I just need a name. What comes after? Yeah, it's likelihood weightage, right? Just from your slides. Do I have space? I do. By the way, earlier, both of you were correct. The probabilities are inconsistent, and that was likelihood weightage. I read it wrong and I wrote it wrong. I skipped a step. Okay.
But if you're rejecting all these samples that you don't need, the probability would still be correct given the evidence, right? Because
Yes, okay. It's still consistent. Yeah, okay. Okay. No, it's this, the correct rejection sampling is consistent, but the one I wrote is just likelihood weightage, which is inconsistent, right? So you were right when you said it then. You are wrong if you see it now. Okay, so the problem is that. The solution is what? I already wrote it on the board. Fix the evidence, right? Solution. Fix evidence. What does this mean? So when we're sampling x1, x2, x3, x4, every time we're checking, wait, is this part of evidence? If it is, I don't sample. I just set it to whatever my evidence tells it is, right? And then I continue. So I fix the evidence. The problem with this, which has also been revealed, is that it's not consistent, or the probabilities are non-consistent. Any idea why? Why are these why does fixing the evidence when I'm sampling deviate the probabilities? Yes?
suddenly if the evidence has a low chance of existing according to the actual probability table, you'd like increase the probability that appears.
Exactly. Think of it this way. Let's say my evidence was whatever, x3 is apple, right? And it had a bunch of other things, right? It had, so it has banana, it has pear, it has apple, and you have whatever, 0.4, 0.5, and 0.1, right? When I fix the evidence, it is sort of equivalent to saying, screw this probability table. I'm going to make this probability table, which is 0, 0, and then 1 for apple. Does that make sense? If this was this probability table, it just literally means fixing the evidence. These probabilities are different. They're not consistent anymore. It changes the Bayesian network, right? So we need to account for it. Does everyone get this? Why this is equivalent to fixing the evidence? Great. So we need to solve it again. What's the solution here now? So now we're nested. Yes? Exactly. Weigh the sample with probability of evidence given its parents, of course. Okay, why does this work? I'm not going to bother. It makes this consistent. Okay, if you weigh the sample, yes.
Do we even have this? Because isn't the whole point is that we don't have definition of probability?
Well, no, well, you don't. But you have instantiated, it's in topological order. So the topological order exists because there's an order in which you can start observing things, right?
But you can't do this for each sample. You have to do it at the end.
No, if you're doing it at a topological sort, all the parents are already done when we come to this evidence.
Yeah, but that's for the topological sort is for each sample, correct? So each sample you start with the parent and then go all the way through, but you
Yes.
don't have the probability given the parent until you have all the samples.
No, okay. You don't need, that's catch-22. When we're observing this Bayesian network, there's a reason it's a directed acyclic. Oh, screw that then. There's a reason it's an A-directed graph, which is you can observe this directly, and then once you observe this, you can observe this and this, independent of the conditional probability table. These are just observations in real life that are happening. And for this to be able to correctly observe this, you need the values before of its parents. Okay, so the observations, that's why I mentioned sampling before. That is fine. You don't actually need any probability table there. All right? Cool. So now you can observe something. So you can sample it with whatever probability you have. Okay. And what next? Is that it? Now it's consistent. Now consistent. Okay. So once you fix an evidence, it sort of influences how you're sampling the rest, right? We want to sort of encapsulate the influence that the evidence has better, right? And to do this, instead, we use Gibbs sampling, right? This is the final, this is the boss of all sampling. And in the easiest terms, it's called walking in E-space, in the evidence space. All right? Not metaverse. What you do, there's 2 steps to this. Oh, there's more. I've just combined it into 2. You assign all variables. The evidence ones you fix, right? So you start with a random sample of all the variables, x1 through xn. And then you resample based on, for each variable, you resample based on the condition of all the other variables. Right? So step 2. Sample xi based on x1 through xi minus 1 and xi plus 1 all the way to xn. So this is manually tweaking just one variable. I have an assignment. I have a sort of like a solution, and then I'm just tweaking one variable based off of everything, the values of everything else, right? Step 3, repeat. Step 2, track transitions. So you keep doing this, and you keep traversing, and then you have these transition counts, which end up giving you probabilities, right? That give you corresponding probabilities. That's it for Gibbs sampling. Yes?
So I'm still confused in regards to how we resample, given that we don't have the probabilities in the first place. We're doing this to get that probability, but we're resampling based on conditionals that we...
OK. I'll tell you what. I'll make a note on Piazza on how sampling works. Cool? Just assume there's a way for you to sample based off of everything else. Cool? Great. All right, we can take a actually, we still have machine learning to go through. OK. We'll take a break at 5. Oh, come on. OK, we're going to start with Markov models and then hidden Markov models. This is the last part of lecture number 8, I believe. And then all we're left with is machine learning. Well, we have a little bit of particle filtering. OK, what are Markov models? Anyone? Yes?
Any model where the next state only depends on the current state?
Yeah, basically. What is the purpose of it? Why do we need Markov models? It's really, really important to understand the reason why we're doing all this. Otherwise, there's...
Is it to like model time?
This model's time. Yes.
Is it to model any system where there is no memory?
Sort of. I'll write it out. We should finish at least this chapter by 5, and then we can take machine learning. Infer the states and change in states. So it must be a dynamic model, otherwise why do we need a Markov model in the first place? Of a system by a sequence of observations. That's what we want to do. Right? So you have whatever, time 1, and then time 2, and so on and so forth. This is sort of a very simple Bayesian network with two things that are different. One, Bayesian networks are finite. This can be infinite, right? We're not specifying anything about its size. And second, the Bayesian network can have, each relationship has its own conditional probability table. In this case, we're going to fix the transition probabilities, right? So there's two things. To define a Markov model, you need two things. You need the initial distribution. So you need the probability of x naught. And then you need the transition probabilities, or the transition model, or the transition table. They're all the same, which is the probability of xt plus 1 given xt. Right? That's the two things that you want. There's a couple assumptions we make here, right? The first one is stationary, or stationarity. What does this mean? Identical. The transition tables, or the conditional probability tables of this Bayesian network, are identical, right? This is the one thing that I mentioned already. And the second one is the Markov assumption, which is xt plus 1 independent of everything else given xt, which, by the way, immediately follows if you treat this as a Bayesian network, right? Cool.
Can you say that Markov models are a subset of Bayesian networks?
They aren't, because Bayesian networks are finite. They're correlated, but they're not subsets, right? Okay, so these are the two assumptions. And now that you have this easy relationship, I will write out an even easier joint probability distribution. X naught all the way to xt is this product. Well, actually, x naught has to be outside, because there's no transition from to x naught. You just started there, right? And then these transition tables. X, whatever, I equals 1 to t, xi given xi minus 1. Right? There's two things we want to talk about. One is convergence here. What does it mean to converge? We're trying to find the limiting distribution of x infinity, right? And what does it mean to converge? It means that when you apply the transition, you get the same probability distribution, right? So you want the limiting distribution p of x infinity. Then you just have to solve this equation. Right? You solve for equality. Right? This is T transpose. I'm actually going to use like a cross instead, because it gets confusing. By the way, this is a matrix. What is this? Anyone? Yes. It's a column vector. What are the values of the column vector? What does each column represent? That it's some particular thing in its domain, right? Oh, wait, sorry, I didn't let you finish.
No,
Go ahead.
I thought it was going to be the probability that a state is something given the previous state.
No, well, but there's no given anything. It's just p of x infinity. So this, let's say there's n possible values, right? So that's its domain. So the probability of x infinity just is a set of real values that add up to 1, right? And there's n of them. So this transition matrix is an n by n matrix. It's an n by 1. And you end up getting an n by 1. You have n values that you want to find, right? To find p of x infinity, you want all n. And you have how many equations? Anyone? How many equations does this give you? N, right? Do you have one more? There's one more from the law of total probability. But that's whatever, right? Doesn't matter. N variables, n equations. Sit, cry, and solve. All right, if this shows up, good luck. All right, but this is how you would solve it. You would do the transition transpose times whatever. So if you had 3, then you would have like whatever. Domain 1, domain 2, domain 3, and you'd have like a 3 by 3 matrix, and then equals domain 1, domain 2, domain 3. You would multiply this out, and you would equate it. You have 3 variables, 3 equations. Go ahead and solve it, right? OK. Any questions before we move on to hidden Markov models? No? Good. Because I wasn't going to answer them anyways. By the way, none of this has been written in that summary sheet. Do you guys want this stuff in the summary sheet? No? OK, cool, great. I don't have to do any more work. Hidden Markov models, HMM. Sometimes you can't observe the xi's directly, but instead you have some evidence for it, right? Sometimes you can't observe that someone has whatever, leukemia directly, but there are symptoms, and then you can use those to infer, right? That gives us a modified Markov model that incorporates these evidences. OK. With this new model, there's a few things we need that we didn't have. So the transitions, that was already fully defined. But now, in addition to the transitions, we have these new relationships. So we need another sort of probability table, right? They're called the sensor. It's called the sensor model. But in effect, it's just another probability table, right? Additionally, if you think of this as some sort of Bayesian network, there's a new set of assumptions that we can make. It's not assumptions, really, but a new set of constraints or relationships that we have. What are those two? They're literally the same thing as stationary and Markov, but for these new variables. Anyone? Yes?
Independent given the variable. The evidence is nothing.
Yep. Evidence is independent of everything else given its corresponding true underlying variable. What else? One more thing. What about the stationary thing? Yes?
The state is in front of everything given the previous one.
No, that's just this. That's the corresponding. That's the Markov one. The stationary. It just means that OK. Every single one of these will depend only on the sensor model, and it's not dynamic. This sensor model is stationary as well, right? So just like the transition model was stationary, the sensor model is also stationary. OK, great. So that gives us our set of new assumptions. And our joint probability changes slightly. You had x0 to xt, but now you also have evidence 1 to evidence t. But don't fret, well, we still have a lot of independences, so we can simplify this very easily. Uh-oh, I keep forgetting to put x0 at the start. Or let's use x1 actually. x1 at the start, and then we can start 2 onwards. 2 to capital T, probability of xi given xi minus 1 times the probability of ei given xi. Right? Verify that this works in your head? Yes.
If we have E1, then wouldn't it be included in this summation? I mean, the product.
See?
We start with X1, we also have E1.
Right, there shouldn't be an E1. There's no evidence for the starting state. Good catch. Yeah, because I shifted x0 as well. That's why. Okay. Does this make sense now? Y, the probability of x1 times probability of x2 given x1 times blah, blah, blah. But whenever E2 comes, as long as you evaluated x2 earlier, you can just write this. So you have these
Is there a reason we don't have this one? Like, strictly speaking, or is it just?
So for the first, there's no transition here, right? This is the initial distribution. We know it. There's no evidence. We know x1. Why would we need E1?
So we're guaranteed to know x1.
Yes. There's three components to a hidden Markov model: the transition model, the sensor model, and the initial distribution, right? So we know this from the initial distribution. Cool. Great. All right. Okay. Now comes something important, something that will actually help, which is what can we do with this? We can do inference. There's 2 main inferences that you want: filtering and prediction, right? I'll write up filtering, and then I'll show prediction. Filtering is you want to find this. Let's say you have all of these observations till time step t, and you want to find or infer what xt actually is, right? So that's filtering. Prediction is sort of similar. You have some evidence from time step t, but instead of figuring out what the current time steps variable is, you're looking into the future, right? So you're trying to find whatever, xt plus k given evidence 1 to t, where k is greater than 0. Usually, it's just 1. Okay? I'm going to write this probability down. If you don't understand it, it's fine. Memorize it. Given xt minus 1. Okay, cool. So this is your observation matrix. Right, and then this is your prediction. Okay, so there's, oh, cool. There's some normalization constants, right, that you're going to have. We'll talk about that later. Actually, we can talk about it now. P of xt, this conditional, is P of xt and E1 to t divided by the probability of E1 to t. That's this, your normalization constant. It's not just 1. You'll have a lot more in your summation, but let's treat it like that for now. What I'm going to do is artificially introduce xt minus 1 and then sum it out. It's the same thing, right? I can introduce a variable and then sum it out. What allows me to do once I introduce xt minus 1 is to break that p of xt, xt minus 1, and e1 to t into this product of two different probabilities. Yes?
Alpha is just the reciprocal of 1 over p of e1 to t.
Correct. This alpha, if you were to only do it for one step. We'll get that, go back to that later. If we do normalization at the very end, it's 1 over p. For every time you broke a conditional into just a product divided by something, it's a product of all of those. That makes up your alpha, right? So introducing xt minus 1 allows you to break up the probability like this. And now we can actually use probability of xt given xt minus 1 just comes from the transition matrix or the transition model. And the probability of xt minus 1 given e1 to t minus 1 is just filtering for the previous step, right? This is the trick. So this sort of actually helps us. Let's write this down, actually. So let's write it here. Oh, quick points. This comes from the sensor model, right? How, given xt, we can find et, right? From the sensor model. That's the whole point of the sensor model. So this observation matrix comes from the sensor model, and then this comes from previous filters and the transition. So when you write this out, if I were to just use f as the probability of whatever that thing is, ft plus 1, let me use just t instead, because we're sticking with t over there, is alpha, then the observation matrix of t times the transpose of the transition matrix, and then ft minus 1. Right? And you'd keep doing this repeatedly. So this is sort of like a nested recurrence. Ft minus 1 would be alpha. Let's add a alpha as well. Alpha t minus 1, ot minus 1, transition transpose ft minus 2. And then keep repeating up until your sort of base case, which is what? Which is f1. f1 is alpha 1, then transition observation matrix 1. But there's no transition. You were already there. You already know the probability, so you can just take the probability of x1. So this is sort of a recursive definition. You'll start with computing f1, and then you would keep doing this. A good thing is these are constants. And for constants, we don't care. We can remove them at the very start. They don't affect the order, right? I can't move the matrices around, because then you get a different answer. But these alphas, I can combine alpha 1 all the way to alpha to t at the very start and just make it a big normalization constant, right? So there's that difference. That's it. So if we have time, you've actually seen an example of this in the tutorial, right? Well, worksheet 12. I've done a walkthrough, so you can take a look there. Cool. Final step, particle filtering. Let's talk about the purpose first. I have the purpose at the end, but what's the purpose of particle filtering? Why not just do something like this? Yes.
This can be very complex, very fast, very expensive.
Why is it complex?
Because you may have too many domains and too many states in the future.
Yeah. So if your state space is massive, where most of the states have a very minute probability that you don't really care about, then what's the point of having this massive table and then keeping it and storing it and working with it? What you can do instead is you can work with a small set of particles or samples and then just propagate it to infer what the underlying transition model is, right? So the sample space might be huge, with many states having just like approximately 0 probability. You can get away with a small number of just particles, and now I'll talk about what particles actually mean, right? But if I do it, you'll see that particle filtering, the time it takes is proportional to the sample size, right? It is independent of how big your state space is. It's only proportional to how many particles you have. Cool. So is it okay if I erase this? Yes? No? No answer? I need 2. Okay, step 1, you're going to initiate n particles. What does it mean? You're going to sample at time step 1 n different particles, right? Whatever it is in the domain, randomly, at random. Next, for each particle, use t to transition. So your particle at time step t plus 1, or your jth particle at time step t plus 1, behaves like, according to the transition model. Particle t plus 1 given particle t, it was wherever, right? So you would transition using the transition model. Step 3, observe evidence. Now, after you've transitioned, you're at time step t plus 1. You can observe evidence at t plus 1. Okay. Actually, I'm going to just put the weigh step here. And weigh particle based on evidence. What I mean by this is based on the sensor model. So if I'm observing whatever, this particular evidence, what is the probability that this particle should belong where it is according to the sample, right? So weight for particle J at this particular instance will be weighted according to where it is in the sample. Cool? Step 4, normalize weights so that they add up to 1 and resample. When you resample, you can resample as many as you want. Usually we just keep the same number. So we keep propagating n through, right? So keep n. Keep n samples. Step 5, repeats. From step 2. This will converge. Yes?
So for the second step, the probability distribution, we kind of make it up.
We have this. We have t.
But the probability that a particle will be in a position given its previous position
is just according to the transition. You have the transition model, right?
Okay,
So you know. So let's say currently let's say it's just true and false. So you have a 2 by 2, right? Given t, you have a t plus 1, you have a 2 by 2. And let's say currently you're in true, then you just have to look at that particular row or column and flip a coin accordingly.
similar to the transition from one state to another.
You transition using t, and you weigh it using the sensor model, right? So we're using the same thing. It's not like the Q-learning where we're getting away without knowing the transition or the rewards. We're using the same thing. It's just a little bit more efficient because our state space can be massive. Cool. That's it. Let's take a break. 5 minutes. Oh, wait, actually, before you guys go. We still have machine learning, so we're going to end up hitting 6 probably. What this means is you guys have the option to go home, do the final. I have a 3-hour office hour on Monday. If I were to say I am going to solve the paper then, would people come?
Yeah, raise your hand for you.
Yes. Okay. Raise your hand if it's yes.
Tell me your hours again.
Good question. It's on Piazza. Can someone tell me when they are? 12 to 3? Yep. Yeah, 12 to 3. Can you guys make it 12 to 3? Please don't make me stay here. Or at least someone has to buy me dinner or something if you're making me stay like overtime. Okay, 5-minute breaks. Go. Welcome back. Welcome back. This is the last lecture. This is probably your biggest lecture too. It had 150 slides. Okay, so machine learning, again with every single topic. Why? Why? Machine learning, why? Yes?
We're not good at drawing lines with best bet.
Speak for yourself. I'm perfect. But hey, I owe you a bunch of candy actually, so there you go. Yo, you guys allow pounce on him after. You know, when you win big at the casino, you gotta be careful. Okay, so machine learning is essentially a way for you to abstract away all the data analysts. All right, we're trying to we have a bunch of data, and then we want to find relationships, patterns, with some general goal in mind. Usually, there's multiple research questions, and the model that we use is very simple. You have some data, so you have some inputs and you have some output. Or actually, let's call this expected output. But basically it says for this, the output is that. Could be something like image classification. Could be something as trivial as, is this a photo of a dog? Right? So if it is a photo of the dog, that's your input, the photo, the output is yes, right? This output could be either discrete or continuous. Discrete in the sense that it could have like categories. So it could be a categorical output. We deal with these and these in many, many different ways. So both of them are very important. Digits are categorical, images are categorical, healthy and sick, right? Leukemia versus no leukemia, or malaria versus no malaria. All of those are binary categoricals. But you also have rating systems that allow for continuous values, right? So if you want to rate a movie, you could have something like, based off of a review, you can generate a 0 to 10 score, which is continuous. Okay, what is the model? This is a little bit about the data that we have. What do? So we take the data. In particular, we take the inputs and we extract features. We extract features. Once we have sort of this list of feature vectors, we then use ML to predict an output, right? And we have this sort of very abstract model that somehow you give it these features, and then it says, this is what I guess Y is. And then if it is, good, the model's working. If it isn't, bad, we have to go and change the model, right? So then if not equal, you go back. Y not equal to y. You go back, you tweak the model so that it can correctly predict based off of x, right? So what are we trying to do? We want y hat to be equal to y for as many input-output pairs as possible, right? We want to, in a sense, we want the probability of y hat equals y given x to approach 1, right? I want correctness. So there's many ways we can interpret the ML model, or machine learning as. And the first one is as a model, right? Naive bias. Now, unlike the hidden Markov model, naive bias is actually a Bayesian network, right? This is the label slash the output. And these are the features, whatever. F1, feature 2, feature n. Well, actually, let's use k features, and let's use n as the number of input-output pairs. OK. What is this? You just treat it like a normal Bayesian network. What can we say about our independences? Anything? Yes?
Wait, sorry, just
You have a question? OK, go ahead.
isn't it supposed to be that the feature is supposed to affect the label?
Is it the other way around?
I mean, the feature affects the label that we get, right? Like the input affects the output?
Yeah. This is from the slides. Can someone just check the slides and make sure the directions are right?
No, slides is the other way around. Slides is like this.
Then that should be correct. Hold on.
The features are the input in the label.
B impacts A,
The feature doesn't affect the output.
probability of B, probability of No direction. How about that? I will figure this out, okay? And then I'll make a note. In the same note that he posts his summary in, I'll add notes. I have to do this, and then I also have to explain how the sampling works. So there's that. OK, some sort of relationship. Regardless of the direction, right, there's still something we can say about this model. What can we say about it in terms of independences, conditional independences? Yes?
So the output is supposed, the label is only affected by the inputs, not the other way?
Yeah. The features are, given the label, the features are independent, right? So Fi independent of Fj given y. And actually, this ends up resolving the direction, I think. Right? The only way Fi given y makes sense is if the direction's that way. OK. That doesn't answer your question. Your answer is y. I'll still answer that on Piazza. OK, so you have this independence. You just treat it like a normal Bayesian network. So how many conditional probability tables do you have here? K plus 1 for y, right? So, well, it's not conditional, so you're still right. You have k CPTs plus just the probability of y. And this is called the prior. All right? It's a prior assumption. So you have k plus 1 tables in this. What do we want to do? We don't have the CPTs, but we have a lot of sample data. We're using the sample data to approximate the conditional probability tables. Right? how? We have a bunch of samples. For every xy pair, I can extract the features of using just x, and then I have the corresponding y. What do I get from it, though? Anyone? I get a bunch of frequencies, right? For each sample, I can figure out the counts. So what would the CPT look like for every single particular thing?
Probability of the feature given the labeling.
Yeah, it's just the maximum likelihood estimate, which ends up being the relative frequency count, right? So if you don't take away anything else, the only takeaway you need is that let's keep this up, actually. Is that the maximum likelihood estimate is equal to the relative frequency count. Okay. So what's the way to use this? Use these samples for any x. Compute the frequency fix. Compute the joint probability table. And then y is the largest. When I say compute, I mean approximate, right? You don't actually have the CPTs. Y is the largest what? It's the largest probability in the joint probability table, right? So once you have the estimate of the CPTs, you can compute the joint probability table, and then what label do you have to give y? Once you sum everything out, it's just the one that's the largest, right? Okay. That's it for naive bias, actually. There's a small segment on overfitting, which I'll quickly talk about, which is the given data might end up overfitting. How does overfitting happen? What does it mean to overfit? Yes?
You have noisy data and
Sure.
the model exactly tries to correlate against the data, which might not make it generally accurate.
That's correct. So there's two ways. One is your data doesn't accurately represent the population, right? And the other is that you have accurate data, but it's just not the entire scope of all possible inputs. It's just a very small partition, right? It's not. The density is not equivalent. It's very dense on a certain subpart. Okay. So how do you handle this? This is C11. You split the data. You have a training data. You don't train on all the data. You have a training data that you train on, and then you evaluate the model on a testing data. Some people also like to have this additional set of data called the holdout, which is for hyperparameter tuning only, right? But usually you can get away with training test. There's also validation. A training test is good enough, right? You don't have to worry about it. Cool. In certain cases, you can actually implement modifications to your model to incorporate this or counter overfitting, right? So it's called smoothing or regularization, right? For regression, you might have seen it as L1, L2 regularization. For naive bias, we have Laplace smoothing, right? So let's write out Laplace smoothing because we're doing sampling, right? So, well, I guess this technically works everywhere. Laplace smoothing K. K is the strength of the prior. And we'll talk about what it means. Strength of prior. If I don't give you any inputs, and I don't give you any outputs, and I give you nothing, and I say, hey, y can be one of these values, A, B, C, D, E, what is the best estimate you can have? What are the probabilities you would assign? Uniform, right? Equal. You don't know. You have no idea. So your prior probability is just equally weighted. Okay? Now we'll see why increasing K increases the strength of the prior. Okay. For every outcome possible, add K counts of it to our frequency. Once I do this, K is, okay, if K is 0, what happens? How many counts am I adding? None, so nothing changes. But usually K is positive, right? Because you're trying to do some smoothing. So if I add one or more to every possible outcome, what happens? Every possible outcome ends up being in our frequency count at least once, right? Okay. And then your probability table would now account, your approximation of the conditional probability table will account these new K frequencies and compute it accordingly, right? For conditional probabilities, one thing I want to mention, the smoothing for each condition happens independently. And this is exactly question number 7, I believe. It's some question on your sample final that we can go over. Condition happens independently. What do I mean by this? So if I'm trying to compute the Laplace with K of x given y, I have the count of x, y happening plus K divided by the count of y happening plus K times not the set of all outcomes, right? The frequency didn't increase for the set of all outcomes. We restricted ourselves to just x. Okay, that's the difference. Cool. Why is this called the strength of the prior? What happens when K approaches, let's say I'm not talking about a conditional, I'm not talking about the conditional, I just want some probability. What happens when K becomes massive, when K increases? When K becomes like infinity, yes?
Then your actual observations don't matter.
Yeah, your observations are so insignificant because you're adding, according to the prior, you're just adding so many observations that it just drowns out any sample data you have. So then if you were to add smooths to infinity, it would just become uniform again. Does that make sense? Cool. That's why it's the strength of the prior. If your prior is uniform, increasing K will get you back to the prior. If it wasn't, if your prior was something else, it would end up converging to that, whatever distribution it is. Okay, next one, perceptrons. I'm going to just stop bringing this down now. Yeah. What are perceptrons used for? Anyone? Yes.
The binary classifier, so it classifies if the object is A or B.
Mm-hmm. It is a linear classifier. It doesn't have to be binary, because when you compute the, yeah, it doesn't have to be binary. If you have some outputs of your perceptron, you can label it many, many ways based on chunks. It doesn't always have to be greater than equal to 0 is 1 and less than equal to 0, less than 0 is 0. It could be, if it's greater than 5, then it's 1. If it's between 0 and 5, then it's 0.5. And if it's less than 0, then it's minus 50, whatever. Yes?
So does perceptron only refer to the outer layer, or can we also call the middle layers of like a neural network perceptrons?
Middle layers. OK, you're getting a little ahead right now, because that's into neural network territory, right? Perceptrons are very simple. They're like the small units, right? But a bunch of perceptrons together will build a neural network. OK, so this is linear classification that we're trying to do. What makes it linear? Well, we compute the features of the inputs, and then we do a linear sum. We do a linear combination with the weights. Right? If it was nonlinear, it would be a nonlinear classifier. OK, so given x, compute fix, compute all the bunch of features that we have. And then a weighted sum dot product fix tells us something about x, right? The features tell us something about x, and then we can combine them using different weights to have an aggregated view of some particular thing, depending on what the weights are, right? OK, this is called activation. Sometimes activation also has an extra term. It's called the bias term. You have bias term W0. And essentially, you can treat it as a feature of the input that always returns 1. Right? So when you do the weighted sum, it's just the weight that gets added to this dot product, right? The output is based on whatever the classification rule is. So if it's binary, then you get a binary classifier. If it's ternary, you get a ternary classifier. It's whatever your output rule is based off of the result of this dot product. OK. I think I'm skipping something somewhere. No, that's after. I'm skipping feature learning way back in Q-learning. OK. We'll get back to that later if we have time. The linear combination reminded me of the. OK, so what is the algorithm? You start with weight 0. So your weight vector. I'm just going to vectorize everything so it's easier to write down. You start with weight 0. Step 2, classify. If you classify correctly, do nothing. If you classify incorrectly, then you update the weight. What do you update it with? You either add the feature vector or subtract the feature vector, depending on whether you wanted a 1 and you got a 0, or whether you wanted a 0 and you got a 1. If you wanted a 0 and you got a 1, then you subtract. If you wanted a 1 but you got a 0, in this binary classifier, you want to add, right? I'm going to rewrite this to something a little bit easier. Plus y star times the feature vector of x. This times is an element-wise times because this is a constant. And this is a vector. Okay. But I haven't defined y prime yet. Okay. Y prime, or y star, sorry. Y star is plus 1 when this is greater than 0. Otherwise, it's minus 1. What does this mean? This means, to classify, I compute this dot product, right? Once I'm done computing this dot product, if it was greater than or equal to 0, what would I classify it as? 1, right, in my binary classifier? But it says I classified it incorrectly. So I predicted a 1, but I wanted a 0. The true label is 0. So I need to do what? I need to adjust, right? Wait, this needs to be a minus. Cool? Does this make sense? You want to update the weights so that it goes down. Or I could flip it the other way around. I can make this a plus and then flip the signs. Same thing, doesn't matter. OK, you want to shift the weights in the right direction, right, for this particular sample. So you're doing this sample-wise. You do one sample. If you classified it correctly, you go next. If this sample is incorrectly classified, you update the weights immediately. And then afterwards, in the next iteration, you use the new updated weights, right? Great. Now this is for a binary class classifier. If you have multiple classes, what happens? What happens in terms of the weights? Do you just have one vector? Yeah, you have a matrix. You have, for every single class, you have a weight vector. Multi-class. Each class C has some weight vector WC. OK. Wait, then how do you classify anything if you have multiple weights? What do you do? What's the classification?
Argmax column.
Yeah. So if you have multiple weights, but you only have one feature vector, you would compute the dot product for every single class, and then whichever one has the highest value is the one that you would end up labeling it as, right? So y hat is argmax y of WC vector dot producted with the feature vector. Cool. OK. That's fine. That's how you're labeling. What if it's correct and what if it's incorrect? If it's correct, you don't do anything. Simple. If it's incorrect, that means it was supposed to be, OK, let's say misclassification. Continue here. Let's say true was label A, and predicted is label B. Does just changing the weight for B work? Does it suffice? Or does just changing the weight for A work? Does it suffice? No, it doesn't. Not only do you need to decrease this weight for B, you need to increase the weight for A, right? If you just decrease the weight for B, that means, OK, B isn't the largest anymore. But what if there's some other label that's also larger anyways? Then in the next iteration, when you come through this sample, maybe the predicted will be C or D or something else, but it won't be A. So you should increase A as well to make sure that A also sort of goes up to the top, right? So that's why you would reduce from B, and you would increase A. There's a very easy way to see why this actually increases the score. The old score was the dot product of WA and this, And when my nu is the sum, when I do the dot product with this sum, the dot product of something with itself is always what? It's always greater than or equal to 0, right? And it's only 0 if all the feature vectors are 0. So usually that doesn't happen. So you'd always increase. And similarly, that's the same reason why doing this guarantees that you will never increase the weights or the activation, right? Okay. Questions before we move on to logistic regression? No. We have 2 minutes of material to go through.
Learning features for the Markov model.
Yeah. What about it?
We didn't cover the
Learning features?
sorry, the feature representation for the Markov model.
Was it for HMM or was it for Q learning? Am I messing things up? Yeah. We'll go about that soon. Okay. Logistic regression. What do we do? What is logistic regression? It's the final thing. Yes.
That was software.
Sigmoid. Yes. So we're trying to view this probabilistically, right? Given an input, given the inputs, there's some probability distribution of what the model can output. And we want to maximize, you want to set up the weights such that it maximizes the probability that for any sample it gives you the right output, right? So you're trying to maximize the probabilities. You want to set weights such that what is this? This is the probability that you correctly label yi given xi, given the weights and the input, you correctly label, or the model correctly labels the input, right? And you want it to do it over all the samples, so you take the summation. You want to maximize this, right? This is equivalent to maximizing the logarithm. Why? I can just, here instead of p, I can just do log of this. Any questions? Wait, actually, there's supposed to be a product here. Whoops. And maximizing this, maximizing anything is equivalent to maximizing its logarithm.
Sum of the logarithm.
Well, I'm talking about this entire thing, alpha. Maximizing alpha is equivalent to maximizing log alpha, right? When you take the log, the product would become a summation. So this is equivalent maximized. This is equivalent to maximizing the summation over I logarithm probability of you correctly labeling the ith observation. Right? Cool. How do we maximize this? For any set of weights, you compute this. And to change it, we need to change it, right? So we need to go in some direction. We need to do some tweaking. So in the set of weight spaces, think of the set of weight spaces as sort of like over. It's like hills and troughs, and the height is essentially that particular value, and any particular point in the lower 2D dimension is the set of weights, right? And you want to maximize it. So if you're at some points here and you want to go to the highest point, right, in the entire world, so what would you do? A good way to do it is look around you and take the steepest step upwards, right? If that was a minimization problem, you would take the steepest step downwards, right? So that's where gradient descent comes in. Gradient descent is just a fancy way to figure out what is the direction of the steepest ascent, because we want to go there. We want to go to the peak. Notice that gradient descent just gives you the direction. It doesn't tell you how long or how big of a step you want to take, right? That's something that's a hyperparameter that's separate. It's also called alpha, but here sometimes it's called the learning rate, sometimes it's called the step size, because it influences how big of a step you're taking. Right? So gradient descents. You want to step towards the steepest direction. Oh, by the way, is the steepest direction the same? For example, if I want to find if I'm in a continuous space, right? And this, let's say that is the way for steepest ascent. What is the way for steepest descent? Is it independent, or I can say it's the opposite? It's continuous. The value is continuous over the weight space. It's not independent. It's just the opposite.
For one-dimensional,
Any dimensions.
So if you're doing gradient descent, our problem changes to minimizing the negative, right?
Maximizing the negative, which is minimizing this value.
But it says maximize the sum over here.
Maximizing A is the same as minimizing negative A.
Yeah, so
Yeah.
minimizing the negative.
Yeah. Does that intuition help? If this direction is the way that maximizes it the most, I just need to go that direction the opposite way, and it will decrease it by that amount, right? As long as it's continuous and differentiable, if you have n dimensions.
Sounds good. You're still able to run gradient descent, you have the subgradients.
I'm not sure. All right, this is beyond my pay grade now. Maybe in a couple of years, once I finish my my master's, you can ask me that. Okay. So you step towards the steepest direction, and that's your steepest direction comes from the gradients. So you derive sort of this g of w. I'm just going to call this a loss function. And you take the gradient and you update the weight accordingly. And this is that learning rate / step size I was talking about earlier. This just gives you direction. This tells you how big of a leap you're taking in that direction, right? Okay, so now there's a bunch of samples. And right now I'm going to give you two different ways to update the weights. One is compute these gradients, right? But don't update the weight immediately. Wait for the entire set of samples. Compute all the tiny, tiny, tiny gradients, and then move in the coagulated direction at once. So I would compute all of these for all the samples, and then in just one step, I would make one jump, right? Versus for every single sample I make, I change the weight immediately, right? One is called stochastic, which is the real-time one. As soon as I evaluate a sample, I update it. The other one's called batch, because I wait for the entire batch of all samples, and then I update it once at the end. What are the pros and cons, and is there a third that I'm missing? Yes?
Isn't stochastic when you take random steps?
No, stochastic is when you...
Once you finish, you jump to the random point. Once you finish,
Yes.
A gradient descent,
But
jump
you
to the
still, in stochastic, you still take immediate steps.
Right.
Yeah. Is there a third that I'm missing? Is there a middle ground we have? Mini batch, right? We have a middle ground. Why? Okay, what are the pros and cons of this at all? So if you do it stochastically, you're updating the weights immediately. So it's very dynamic. It's quick computationally, right? You're getting, instead of waiting for all of this, imagine if for every sample the gradients sort of like were different and they sort of ended up sort of canceling out. What do you do then? Right? That's a problem. So if you're updating at every single step, at least there's the illusion of progress. It's not illusion. It will be a little bit quicker. But batch updates are more accurate because they take into account all the samples in one step, right? Before they make a step. So they have like a sort of, it's like the wise old guy. It's a turtle and hare sort of thing. And mini batch finds the middle ground for this. There's one more thing I wanted to say. What was it? I forgot. OK, then. Next, you have neural networks, which we're not going to cover. So that's it for this review seminar. I know I have to do the feature-based approximate Q-learning. And OK, sure. Let's do it very quickly. Why do we need it? Again, because state spaces can be massive. If I have features, I can bring down the state space and represent the entire problem using just a smaller set of features. I think the example used was chess. Chess has 10 to the power 43-ish states, but we can work with a 30-feature sort of model pretty well, right? There's some weight updates, and there's the Q value update in there. And then there's policy evaluation. All of these should be fairly straightforward. Just memorize them. There's probably just like 4 formulas. OK, cool? Great. Thank you so much for coming to this review seminar. And I'll see you guys on Monday.